So we've got two good looking trees right here, and it would be really nice if they had some animated particles for leaves that would fall from them and move around. It's about time for us to get into some actually nice looking visual effects for the game, and to do this we'll be using particles, as I've mentioned. Oftentimes particles refer to just still images that'll float around, usually pretty small ones at that, but in our case what we'll be doing is using animated particles where it's playing an animation, and then once the animation is complete they disappear. So they can be used for more than just like tiny little leaves that are floating around and stuff. We can use them for just playing animations if we want in a specific location. So the first thing we'll need if we want to have leaves falling from our trees is to know where to spawn these particles from. So to do this, we need to figure out where our trees are, and then kind of create a hitbox to spawn our leaves from. And as always with Pygame, you're pretty much doing this all yourself, so we'll have to create all of the code for generating that area and figuring out which locations can spawn leaves based on the areas that we have and stuff like that. So let's get into it. So in order to get the position of our trees, I think it's best to go to the tile map, and we'll add a new function here that can be used for a lot of things. So let's call our function extract self, and it'll take the argument ID pairs, and then keep equals false. So what this function will do is it will take a list of ID pairs. So this is, if you remember, our tiles are in a like tile type format along with a variant. So it's type and variant, and those go together to uniquely identify the tile type. So that's what I'm referring to when I say ID pairs. More specifically, an ID pair is one of those two combined. Now, the ID pairs is a list of those, and we'll check if a tile is in that list. And if it is, then we can return it. So what this function will do is it will take a bunch of types of tiles that we're looking for and tell us where they are and give us information about them in our map. And then if we want, is what this keep variable is for, we can have them removed from the map. So we're not going to need that yet because we do want to leave the trees hanging around in the map, but later when we do some other stuff, we might want to get rid of things. For example, if it's an entity spawn location, we might want to remove that from the map and then create an entity. Alright, so to do this, let's create a list and call it matches, and then we can iterate over our tiles in our off-grid tiles. Let's do this one first because it's easier. And then the reason we're copying here is because we might want to delete from this list if we're not keeping. So we'll do if, and we'll make the tuple here for the ID pair, tile type, tile variant in ID pairs. That means that we've found one of the ID pairs that we're looking for. Then we'll do matches.append, and then we'll say tile.copy. So just give it the tile information. Alright, now if we're not keeping our tile, then we want to remove it from our off-grid tiles. So that's pretty much the logic for that. Just look for the match, add it to the results, remove it if we don't want to keep it. And then we gotta do the same thing for the tile map. So we go through the locations, and then we say tile equals self.tile map location, and then we do the match. So tile type, tile variant, in ID pairs, matches.append, and then just another tile.copy. And then this is a little bit different. We'll have to do matches -1 position equals matches -1 position dot copy. So what we're doing here is we're going to change this position attribute, or not attribute, it's actually a key value pair in the tile dictionary, but we're changing the position for the tile that we're referencing because we want it to be in pixels. If you remember, the tile map is in tile coordinates for the grid, not in pixels, so we want to convert that. So to do that, we'll do matches -1 position 0 multiply, and we do self.tile size typos. Alright, and then we do that for the y-axis as well. So that gives us the pixel coordinates for our position. The reason why we do copy here is the same as up here. We want to have a copy of the tile. We don't want to be working with the exact same thing. And then over here we copy again because copy is just surface level. if there's a list nested inside of something, it won't actually copy that. It'll have the same reference. So this is just making sure it's clean. There's a function called deep copy that we could have used that will do basically these two things in one line, but I don't want to really get into that. So basically we're just making a clean copy of the tile data, because what would happen if we didn't is if we modified that tile data after getting the results, it would modify the actual tile in the tile map when we don't want that. And then, like I said, we're converting it to pixels. So now we can do the if not keep. We do del self.tilemap location, and then we can return our matches. So now that we have our function here, we can grab this and we can go over to the game, and then we can say print self.tilemap and then we extract, and then for our ID pairs we'll use a list with just the single pair of large decor 2. So if we wanted to get another type of decor, we could just do like this and say 1, but this will work for now. So we say large decor 2, and that will just match with this one tile, and then it'll give us all of those results. So we want keep to be true because we don't want to remove the trees, and then that will give us the results of all of our matches here. So I run that, and then we can look down here and we see type large decor variant 2, and then here's the position we're looking for. So it's got all of this useful data, and then from this we can figure out where we can spawn our leaves. So I'm going to use a bit of a hack here. There are better ways to do this that are more general, but for the purpose of this project, I'm going to keep it simple and just kind of hard code a hitbox based on the location, because we only have one type of tile that can spawn leaves. So let's do something where we have self.leaf spawners equals that. And then we can do for tree, and this will be the tiles that we were returning before. We can do self.leaf spawners.append. And then for our hitbox, we'll do a Pygame.rect, because if it's a rectangle, Pygame.rect has a ton of useful functionality for that type of thing. So for that, we'll say for plus the tree's position on the x-axis, and then for plus the tree's position on the y-axis, 23 and 13. So you can go look at the dimensions of the tree image if you want. This is just taking the position of the tile and just kind of looking for the area of the tree image that it makes sense to spawn leaves. So we're actually offsetting it by 4 from the top left to the right, and then same thing down from the top left, because we don't want to start right in the top left because that's technically air. So this is just the rectangle that makes sense for that image. You can go look at it and just draw it out if you wanted. So we can now print out this list, self.leaf spawners. And remember, the rect is x, y, width, height. Anyways, so we can print out our leaf spawners and close again. And we have our 2 rects here representing our 2 trees. Since we have our rects where the leaves can spawn now, we could theoretically easily pick locations to spawn the leaves, but now we need to be able to actually have the particles that we're spawning. So to do that, let's go ahead and make a new script. We'll call it particle.py. And this is a pretty basic one. So we'll do class particle def init, and then it needs access to the game. We can do self.game equals game. And then we want the particle type. We want the position. We want the velocity. We'll default that to 0, 0. We want the frame that we want it to start on. All right, so we can do self.type equals ptype, self.position equals list position. And remember, that list is just making a copy. All right, so, and then we can do self.velocity equals list velocity. And then self.animation equals self.game.assets. And then we'll take particle, and we'll have to load this in a moment. And then we'll take the particle type, and then we want a copy of that animation, and then self.animation.frame equals frame. All right, so that's the setup for our particle, because the particle needs to be able to move around, and it needs to have a velocity so that we can configure how it moves. And it has the animation, and that's really all you need. Well, also the type, obviously, but that's really all you need. Now we can just do def update self.position 0 plus equals the velocity. This is just the basic stuff, so we do the y-axis too. And then we need to do self.animation animation.update, and we'll do kill equals false if self.animation.notFrame done kill equals true. So our update function is going to do a couple things here. We'll return kill. It needs to determine when the particle needs to disappear, so that's what this kill variable is for. As soon as this update function returns true, that means that this particle needs to be removed. So we return true once the animation has finished playing, which was what we added before. This is a nice little utility attribute that we have for that. And we also have to update the animation in our update function and move the particle. So there's a couple things. If we wanted, we could add more behavior here as well, but it should be enough for now. And it's really important to remember the type of thing you're pulling from the assets here. Like for example, if this were a list of images, you'd probably have a problem, but we will be adding this in as an animation like we did for the player stuff. All right, so now we need one more function for a particle. We'll call it the render function. It needs a destination surface and an offset, and we'll take 0, 0, and we'll take image equals self.animation.image, and we just take that, and then we go surf.blit. We render our image onto the destination surf at the position we have, minus offset 0. And then this is something actually we're doing. I like to center my particles based on the center of the image instead of the top left. It just makes the behavior easier to work with and more aesthetically pleasing. So let's do minus image.getWidth, and then we divide that by 2. Now we can do self.position1 and just the whole thing for the y-axis. All right, so now we have the rendering coordinates for the x and the y-axis, and that should be sufficient for our rendering function. All right, so now we need to actually add our particle assets, and for that, we can go back to our assets thing right here and say particle/leaf. And that's the particle type we'll be using. If you remember, we said particle / and then the type, and we'll be using leaf here. So we'll create an animation of load images, and then we'll do entities, particle leaf, I believe. Let's check that. So we go data, images, we have particles. So this will be particles/leaf. So we have 2 types in here. We'll be using just leaf for now. In here, there's 17 images. If you look in here, there's like different leaf images. Normally in my games, I would have the ability to recolor these, but right now we'll just be playing the animation and that's it. So it'll play through those leaf frames, which will load here and then attach to the particle. And then we'll have our particle as we wanted. So now that we have the particle object, I think it's time that we add our particle collection. So we can say self.particles equals that list. And if you remember, we had that return kill thing in the particle code. So in our loop here, we need to keep track of that and see if we need to remove it. So we'll do for particle in particles.copy. And again, we're doing the copy thing. We're doing the copy thing because we will be removing during iteration. So kill equals particle.update. So we're calling the particle.update, and then we're just checking if we need to kill it. So we can do if kill self.particles.remove particle, and that will handle that. We also want to render a particle, so particle.render, and then let's do self.display offset equals render scroll. All right. So we now have our collection of particles, and it should remove them as soon as the animation is played through. So now we just have to spawn our particles. So for that, let's look through our leaf spawners. So for rect in self.leaf spawners, if random.random, and this is going to be just a mess of numbers here, 49999 is less than rect.width by rect.height. I'm going to go import random here because we don't have that. Import random, and then we also want our particle. So from scripts.particle import particle. So if you're unaware, random.random is just a random number between 0 and 1. It's a floating point number, so it could be like 0.25 or something. And then we're just multiplying it by this and then checking it to see if it's less than the pixel area of our rectangle. So this is a way where you could have the spawn rate for leaves be proportional to the amount of pixels that that hitbox covers, so that if you have like a bigger tree, it will spawn more leaves. And then this number right here is just to control the rate at which they spawn, because if you do this, it will spawn 100% of the time, like every single frame. So by multiplying it by that big number, it'll make it so it's not every frame. Anyways, if we've decided that this random odd chance has passed, then we can say our spawn position equals rect.x plus random.random by rect.width, and rect.y plus random.random by rect.height. And this is really one of the more interesting problems, I think, in this tutorial. It's just the spawning leaves problem. So there's a lot of random techniques you can pick up from here and different ways of solving problems. Of course, this doesn't generalize to that many different things. So there's just little things you could start thinking about here and there about how you would approach problems. Anyways, so we're taking the x of our rect and then adding the width multiplied by a random number from 0 to 1 times that. So that will give us any number that's within the bounds of the rect, because 1 times the width plus the left position will be the right position, and then 0 is the left. So anything in between is somewhere inside. And it's linearly distributed. So we can do self.particles.append, and this is where we spawn our particles. We do particle, and we do self to pass along the game. We want the leaf particle, and then we'll give it our position. So that will be position, that which we just calculated. We'll do for velocity. All the leaves will have the same velocity. You could randomize this if you wanted, if you want variance, but I'm going to leave it at -1.3 or -0.1 and 0.3. That will mean it's going slightly to the left, but mostly down, but also very slowly. For the frame to start on, we'll say random.randint. If you don't know, this is a random number within, I think it's inclusive of the two numbers we give it. So we'll give it 0 to 20. So that will select just a random frame for it to start on. So that way we don't always start with the biggest leaves. Anyways, so that will spawn our particles, and then this will manage our particles. So if we did everything right, it should work now. Aha, so you can see there are leaves falling now. They're a little bit rare, but as a visual effect they should be. Oh, I do see we have a problem though. So first of all, our leaves are kind of decaying into the 1 pixel dot very quickly, and then second of all, the animation is looping and they're not disappearing. So to deal with that, we need to go over to our animation here, and if you remember, we have a couple of options here for animation. So first of all, we need to make them decay slower, so we'll do image duration equals 20. So 20 frames for each frame of the animation. It's confusing terminology, but whatever. And then we want to disable the looping, so we'll do loop equals false. So we run that again, and we have leaves that are decaying much slower. It looks much nicer, and we're looking at this one on the bottom left, and the one, it just disappeared. So our leaves are disappearing, that's good. They're decaying slowly, that's good. So looks very nice, but there's one more effect I want to go ahead and add over here. So if we go over here into the particle management, we can add some extra rules for our particle. We already have our update function, but we could do something else if we wanted. So we can say if particle.type is leaf, then we can say particle.position 0 plus equals math.sign particle.animation.frame by 0.035 by 0.3. All right, so we do need math. That's the math library that comes with Python. And that's just giving the sine function to us. So if you don't know what the sine function does, just think of a sine wave. So you know the curvy wave that goes up and down. You can just look up a picture if you want. And we're passing in just the animation's frame, so like the progress that we have in our animation. So if you know what the sine function does, it will give you a number between -1 and 1. And it will smoothly go between the two. If you were to plot it out, it would be a kind of a bit of a smooth curve. So it has a more natural pattern than just moving to the right at 1 pixel per second and moving to the left at 1 pixel per second. It will slow down as it gets to the edges. So what we're doing here is we're applying this random number that could be -1 or 1. Well, we're multiplying it by 0.3 to decrease the force of it. But we're applying that to the position. And because it's a number between -1 and 1, it actually sums up to 0 over time. So what this is doing in the short term is it's making the particle move back and forth, like right and left over time in just a smooth pattern. So this last part here, the 0.035 thing, is just to make sure that you don't go through a whole kind of loop of the sine function too fast. It's just to slow down how fast it goes left and right. And if you aren't aware, there's no limit to how big of a number you can put into the sine function. It will always give you a number between -1 and 1, so we don't have to worry about how far along that is. Anyways, if we were to run it again, we could see that our particles will move right and left now. So if you watch this particle closely, it'll like sway back and forth, right and left. So this is a technique I use for a lot of things. If you want natural animations for a variety of things, the sine wave is a really good way to get a natural look. You can layer it with some other stuff because technically it's a little bit too mathematically perfect, but it's more natural than the robotic adding -1 or 1 technique. This is a lot smoother, but that's just a useful thing to keep in your toolbox. I recommend getting very comfortable with this function. If you just play around with it, you can get an idea of what it returns for different values, and you can get used to using it for things. Of course, it has tons of other applications in math as well, if you've taken trigonometry, but I won't get into that too much. So if we go back over here to the input code and take a look at our up arrow key, we'll see that we left it as you press up, the velocity of the player is just set to a negative number. So the effect of that is that if we run the game, you can just press up as much as you want and jump as much as you want. So normally in a game you wouldn't want this, maybe if you're playing Kirby, but for the most part, you don't want to be able to just jump to infinity. So what we'll be doing is we'll be adding some restrictions on jumping, and then also while we're at it, we'll add the wall slide effect so you can slide down a wall and then jump off of it. Alright, so let's get started with the easier part, which is the jumping aspect. So what I'm going to do is I'm going to go right here in this key up part and just swap this velocity change with player.jump, and then we'll fill out this jump function so that it handles the jump when the button's pressed. So we can just go over to our player here and we can add a new function. We'll go def jump self. We don't need any arguments. Alright, pass for now, and we need a couple of things added to the player to keep track of jumping. So we need self.jumps equals 1. The way I'll be doing this is that the player will have one jump, and a wall jump will consume that one jump, but if you run out of jumps and you're on a wall, you can still wall jump. So you can jump and then jump off of a wall, but if you fall and jump off of a wall, you can't jump again. That's just my preference for how this is implemented here. You could come up with all sorts of rules for how you want the jumping limits to work. If you want, you could just increase the maximum number of jumps to like 3 or something, so you can jump in the air 3 times. You can do all sorts of fun stuff. And I recommend you do play around with that if you want to get a good understanding of how this works. Anyways, so let's go over to this jump function. We'll need to keep track of this jumps attribute to determine whether or not jumps can be made. So let's do if self.jumps minus equals 1, self.velocity 1 equals -3, and self.error time equals 5. So we're doing a couple things here. First of all, we're reducing the jump count. So if our jump starts at 1 and we jump and reduce the number of jumps by 1, it'll go down to 0. And this statement will fail the next time you try to jump, because if jumps is 0, that evaluates to false, so you don't have any jumps left and you can't jump. Anyways, but it'll also modify the velocity, same as before, -3. And then while we're at it, we'll set the air time to 5. That's just to force it to automatically transition to the jump animation, because once the air time is above 4, it'll transition. Otherwise, you would have to wait like 4 frames, so you get a little bit of the running or idle animation before it actually switches to jump in the air, unless you have this line. Anyways, The next part is to actually restore your jumps after you've hit the ground, which is usually what you want to do. But I mean, you could make a mechanic where you have to maybe collect something in order to restore your jumps, and your jumps are a limited resource. But in our case, and with most games, you'll want to make it that when you touch the ground, you restore your jumps. So we'll do right here, when you collide with the floor, going downwards, you can do self.jumps equals 1. And if you wanted to have 2 jumps, you could just swap these 2 numbers for 2, and that would make it so that you always have 2 jumps after each touch with the ground. Alright, so that's the basics of keeping track of your jumps. If we go over to the game, and if I press up twice, you'll see that I can only jump once. If I press the key loud enough, you might be able to hear it. But yeah, well, now if we go back over to here, we can go ahead and start working on the wall slide. So to do this, we'll add a attribute for, wall slide, and set it to false. Now this is where things get a little bit messy, because not only do we have to deal with the actual movement mechanics of dealing with a wall slide, and the jumping resource management of a wall slide, but we also have to deal with the animation aspect of the wall slide. So there's a lot of components going on here. So this is going to be a bit more complicated than just the number of jumps that you have. So let's start by saying every single frame will say the self.wall slide equals false. And the purpose of this is so that this variable will act as a single frame switch, or like, I don't know, a button where it fires off an event once you press it. That's sort of how this is set up. So once you set it to true during the frame, it'll be true for the rest of that frame, but then when it comes back to here on the next update, it'll be false. So this is a useful trick if you want to have something that that's sort of an event that fires off once. So now we'll write the part where we'll determine if wall slide should be set to true. So we'll do if self.collisions right, or self.collisions left, and self.airtime is greater than 4, self.wall slide equals true. So what we're saying here is if we hit the wall on either side and we're in the air, and this is the threshold that we're using to determine if we should be showing the jump animation, but if we're in the air and we're touching a wall, then we should be sliding on that wall. So since we're using this technique where we basically set it to true and then switch it back to false every single frame, then we're basically saying only for the frames where this holds true will this be true. What you could also do is you could throw an else right here and say self.wall slide equals false, but this works as well. Now we can do self.velocity1 equals the minimum of self.velocity 1 and 0.5. So what we're doing here is we're capping the downward velocity at 0.5. Remember, the min function takes the lower of the 2 values, so if this number is lower than 0.5, it'll take it. If it's greater, it'll take 0.5, so that's just a 0.5 cap, effectively. Now, let's do if self.collisions right. So we need to break apart this statement here, because while this is the statement that determines if you're sliding on a wall, we need to break it down to determine which direction so that you can show the correct animation. Anyways, so we can just check if it's right, and if we know if it's not right, then it must be left, because that's how an OR statement works. Anyways, we can do self.flip equals false, and this is important for keeping our animation accurate, and then we can do else self.flip equals true. And remember, the base images for the player are facing right, which means that we want flip equals false when we're facing right, and then flip equals true for facing left. Anyways, now we want to do self.setAction wall slide. And now the purpose of this wall slide variable, because if you think about it, we have most of the code here for handling the effects of the wall slide. So we're updating the animation, we're handling the flip, we're restricting the velocity. So this variable right here is just for a couple of things. It's used to prevent the animation set right here from being overridden by these ones. So we can go if not self.wall slide. Because if you're sliding on the wall, you don't want it to switch to whatever the normal animation would be. And because of this restriction right here, it would technically be either you're in the jumping animation or wall slide, because this is the first case. But we can just break it all out and say, if we're wall sliding, don't do any of the other animations. We want to show the wall slide animation, which is whatever it was previously set to. And then once that becomes false, which will be as soon as you're no longer touching the wall, then it'll let it switch to the other animations again, which should probably be jump. Alright, so now that we have the animation side of things handled, and the slowly sliding down the wall side of things handled, we can go ahead and work on the jumping part of the wall slide. So we want to make it so you can jump off the wall. So we'll do this by doing if self.wallSlide, and that's why we need this variable over here as well as an attribute. We'll do pass, and then this will become elif self.jumps, because we want to prioritize the wall slide first over the normal jumps. And then we'll say if self.flip and self.last movement 0 is less than 0. So what we're looking for is flip equals true, which means you're facing left, and your movement that you attempted to do is going to the left. Then self.velocity 0 equals 3.5. So that's going to add a velocity, almost like an impulse, pushing you to the right, which will push you away from the wall. And that's the jumping away from the wall part. So now the other part is the vertical component of the jump. So self.velocity 1 equals negative 2.5, and that will force you up. Same as the negative 3 here, except in a wall jump, you probably don't want to jump as high as a normal jump because you're also going to the side. Anyways, we'll do self.air time equals 5 just to get the animation updated. And we can do self.jumps equals max 0, self.jumps minus 1. So we want the jump to be consumed if you have one remaining by the wall jump, but like I said before, you should still be able to wall jump if you don't have any jumps left, which is why there's no check for the number of jumps you have before it gets to the statement. And then something you have to be careful about is because we're doing if self.jumps and not if self.jumps is greater than 0, then we have to make sure that the number of jumps can't go below 0. And technically, if you can wall jump when you have 0 jumps left, and you subtract 1 jump from there, it would go to negative 1. So that's a bit of a tricky bug that you don't want to deal with. So we max these two values so that the minimum value is 0. And that will effectively just only reduce your jump if you have them left. So now we need to deal with the other direction. So elif not self.flip and self.last movement 0 is greater than 0. And then we just kind of copy all of this, and there's better ways to do this, but this is good enough for now. And you just swap that direction on the x-axis, and that covers everything. Alright, so that is our jump code. The last thing I'm going to do, and this is just for convenience if you want to add something on top of this, is I'll add a return true if the jump actually occurs, so that you could hook off some events from this jump function. So you could go over here and say if self.player.jump. So if the jump actually went through, then you could do something else. So normally in my games, I might add in a special animation for that, but I think I'll leave this for now, and you can go add that yourself if you want. Anyways, let's go back over to our update function. If you notice, we modify our velocity here in 2 dimensions. So we have our code for the gravity that runs up here in the entity parent class for the player. It will force the player to fall downwards and then cap it at 5. So that will make it so that if you're jumping up, it'll pull you down, and you've seen that already. But if you notice, we don't actually have any code for normalizing the x-axis. So if you were to jump off of a wall and have your velocity set right here to like negative 3.5, it would stay at that number and you would just constantly be moving left. And we don't want that. So to deal with that, we'll need to add some normalization to the horizontal velocity. And that just means that we're going to be making it move towards 0 so that it eventually gets to 0 and you stop being forced in that direction. Similar to how gravity will pull you down. You can think of this like air resistance. That's sort of what it's like, except technically we're exaggerating it for the sake of gameplay. So we'll do if self.velocity 0 is greater than 0. Self.velocity 0 equals the minimum of self.velocity 0 minus 0.1 and 0. So what we're saying Actually, so this should be max. So what we're saying here is that we want to subtract 0.1 from the velocity every frame if it's greater than 0, and then stop it from going below 0. So you just want to stop at 0. And then that will make it so that it brings it towards 0 if it's greater than 0. So we have to deal with the other side now, which is if the velocity is negative. So all that is you just take this, you copy it down here, you switch this to plus, and you switch this to a min. So that will make it so it'll take the two values and say which one is lower. So as soon as this number crosses 0 into the positive territory from these increases, it will get capped at 0 so that it can't actually go over. So this will just pull the number linearly towards 0, and that will give us the effect we're looking for. So if we go ahead and run our game now, we can run around, we can jump, and if we go over to a wall, we can slide down it slowly. Oh, and we've got a crash here. So it appears that I have not added the last movement attribute. So that's just a simple concept. The idea is that you take whatever the previous movement was and do something based on that. So to add the last movement, we can just go over to our physics entity, and we can say self.lastMovement equals 0, 0, because remember, this is what we're inheriting from as the player, so it'll have access to everything in here. And then we can go over here and then copy this down into this update function, which takes the movement, and then we can just drop it right here and say that the last movement equals the movement. And now we should have this last movement attribute to work off of for our jump mechanic. And something important to note is that this movement variable is keeping track of movement, which is the input to the update, not the actual movement that was executed upon. So if, for example, you're running into a wall, it'll keep track of the intent to move towards that wall and not just put it as like 0 on the x-axis because you hit the wall. And that helps us keep track of the fact that we're actually trying to push up against that wall. Now if we run over to our game and we run it and we jump into a wall and we try to wall jump, it works properly. So it bounces us away. Jump up, bounce off the wall. Works as intended. So you can jump once and then you can jump off a wall, or if I go up to here and then slide down the wall and jump, that's our only jump. So that's how we intended for it to work, and it's working as intended. So these two things will cover pretty much all that we were looking for in terms of movement, at least in the jumping sliding space. There's one more thing that we have left for movement. Let's go ahead and add the dashing mechanic to the game. This is not only a movement ability, but it's also how you do the combat in this game. The enemies will shoot at you while you as the player have to beat them by dashing through them. So it serves multiple purposes. For the effect, we'll have to move the player suddenly, and we'll also have to have some nice visual effect to go along with it. So what I'll use is a burst of particles. So let's start by loading in the particles that we want to use. Let's grab the particle leaf. Let's copy that, and we'll say particle. And then for the image duration, we'll say 6 instead of 20, because this particle should not last nearly as long as the leaf. So if you look in our particles list, we do have this particle, which is just 4 images, and they're just circles. So I'm going to go ahead and close that though. So now that we have our particle animation loaded, we'll want to add the key binding for actually using the dash. So let's go down over to our keys here, and we'll do if event.key is pygame.kx, and that will be your key that we use to dash. We'll do player.dash or self.player.dash, and similar to the jump thing, that's something that we'll have to go ahead and add here. So let's go over to the player, and we'll go under the jump code, and we'll say def dash self. And this will be a pretty short function. We'll do if not self.dashing, which is something else we'll need. Let's go up here and add it. Self.dashing equals 0. If not self.dashing, so self.dashing is 0, we can do if self.flip. So that's if you're facing left, self.dashing equals -60. And then we'll do else equals 60, and so that's if you're going right. So this dashing variable will keep track of how much we want to dash and in which direction. So 60 is how long we're going to dash for, and then this negative is for the direction. So you know how there's the idea that velocity is not only a speed, but also a direction? That's what we're using here. We're using that directional component to say which way we want to dash. So that's just a nice convenience that we can use. All right. So now we have to actually do something with this dashing variable. So we need to do something that says basically if it's not 0, then we need to apply the dashing effect. So for that, we can go up here into our update function. We can just go right here, I guess. It could go in a lot of different places here. So self.dashing is greater than 0. We'll do self.dashing equals max 0, self.dashing -1. And this should look familiar. That's the same thing we're doing right here. So this is just bringing it towards 0. So we need to manage our dashing value so that it just goes down towards 0 and that the effect can eventually end. So the other side of that's going to be the +1 with min. And then now we can do some other stuff. So what we'll say here is if the absolute of self.dashing is greater than 50, self.velocity 0 equals the absolute of self.dashing divided by self.dashing by 8. So what we're doing here is we're saying if we're in the first 10 frames of the dash, then we take this part, which is actually just, it's going to be 1 or -1, depending on which direction it is. So if you just divide the absolute by its own value, you'll get the direction of the scalar. So in our case, if it's a positive number, you'll get 1. -1 will be received when you have a negative number. And then that will just be multiplied by 8. So we're just modifying it based on the direction here. All right. So now we can do if self.dashing is 51, self.velocity 0 times equals 0.1. So what we're doing here is that at the end of these first 10 frames of our dash, we're going to severely cut down on our velocity. And this remaining velocity will be quickly just diminished by this code right here, which will reduce the velocity. So the purpose of this is to just kind of cause a sudden stop to the dash. If you saw it from earlier, you dash suddenly, and then you stop, but there's a little bit of velocity left over. And that's how we can achieve that. So you might be wondering, okay, that's the first 10 frames, what are the last 54? So this is also not only working as our code for applying the dash, but it's also working as our cooldown code. So when this number is less than 50, but still greater than 0, if you remember, in order to dash, dashing has to go down to 0. So this is actually working as our cooldown, so that you can't dash as much as you want. So remember, this will eventually bring it to 0, but this is going to be 5/6 of a second before it goes completely to 0, so you have that little bit of time of a cooldown where you can't dash again. So you can't just dash as much as you want and basically fly around. So that's how we manage that. So I can run the game now and show you what this looks like. So I can run around, and if I press X, I can dash around, which is cool. Now it's time to add some visual effects to it. This just handles the movement component. And let's go over to entities here. Let's close this. If you remember, our physics entity up here has its own render function right here. So I want to make it so that when we dash, we turn invisible. And we just turn into kind of a stream of particles. So what we'll do is we'll take that render function and override it right here. We'll say def render, well, not override it, we're going to build on top of it. We'll take our surf and offset, and we'll do if the absolute of self.dashing is less than or equal to 50. So remember, this is accounting for both directions. You're saying if we're not in the first 10 frames of a dash, basically if the dash is on cooldown, or if it's just completely off of cooldown and we're not doing it at all, then we can go ahead and do super. So this is accessing the parent class and .render, and we'll pass in the surf and offset equals offset. So what we're doing here is we're kind of gating the rendering function of this physics entity, which we would normally be using, behind just an extra layer in the player that checks to see if we're dashing or not. And if we are dashing, then we don't want to actually render it, so it'll skip this, and it just won't show the player. All right, so that will make the player invisible. So the next part is the particles that I talked about earlier on. So for that, there's two sets of particles I want to do. So first, I want a burst of particles when you first start and when you end your dash. And then I want a stream of particles while you're dashing. So to do that, we can go ahead into our update function here. And right here, we can just add the code for particles. We can do self.game.particles.append. And this is where we can add a particle if we want. So for this, we need to actually have particles to work with. So let's go over up to the top and we'll say from scripts.particle import particle. And while we're at it, I'm also going to grab the math module because we're going to be doing some trigonometry here. All right, so let's go back now that we have our imports done. We can work on spawning our particles for this. So like I said, we want a stream of particles just as the player's dashing. So for this, we can do particle, and then we'll pass in self.game, and we'll say it's a type particle, and we want to spawn it from self.rect. And if we go up here, that's this function here that generates the rect for the player. And we want to take the center of the rect, so this will just be a tuple, just the x and y coordinates of the center of the player. And that will be our spawn location. And then we also need actually, let's split this up here. So we'll say velocity equals, or I'll say p velocity just to distinguish it. So p velocity equals the math.cosine of an angle times a speed, and then we want the math.sine of an angle times the speed. And for this, we'll go ahead and say angle equals random.random by math.pi by 2, and our speed will be random.random by 0.5 plus 0.5. And then now we can take this p velocity here and say velocity equals p velocity, and then we'll also want frame equals random.random 0 to 7. All right, so what we're doing here is we're taking the cosine of a random angle. So well, first of all, let me import random real quick. So let's go import random. We're taking a random angle. This will be random.random times math.pi times 2, if you know how radians work. This is just the full circle of angles in radians. Like a full circle is math.pi times 2. And this random.random is just selecting a random angle within that full circle. If, for example, you were to just take times 10 or something, you would get it unevenly distributed because there's certain sections of the circle that show up more in the numbers 0 to 10 in radians than others. That's why you want the exact amount of math.pi times 2. Technically, if you were to just put in a really big number, it would be almost the same, but this is the technically correct way to do it. Anyways. So this will just get a random angle in a, like, think of a circle, just pointing in a random direction. And then we'll take a random speed, and this will be just a random number between 0.5 and 1. Because remember, random.random, 0 to 1. So you take that, multiply it by 0.5 and add 0.5, and you get 0.5 to 1. All right, so for p velocity, we're taking the cosine of the angle times the speed, and the sine of the angle times the speed. The cosines for the x-axis and the sines for the y-axis. This is a little bit of trigonometry. So what this is doing is it's generating a velocity based on the angle. And this is how you move something in a direction, in any case, pretty much. At least in 2D. In 3D, it's a bit more complicated. But in 2D, you take the cosine of the angle you want to move, and you multiply it by the amount you want to move for the x-axis. And then for the y-axis, it's the sine. And if you've taken any trigonometry, you would know about the whole opposite and adjacent sides of a triangle and their associations with the functions of cosine and sine. So there's actually math behind here if you've looked into trigonometry for how this all works, but it can get a lot more complicated than it needs to be. So you can actually just pretty much memorize this one statement right here, or this one formula, and this will get you through most of the trigonometry you need for games, in fact. I have a video about this topic as well if you want to get into it a bit, but this will cover most of what you need. The other half of what you need is using arctangent 2 to turn an x and y coordinate into an angle. So it's just the conversions between angles and Cartesian coordinates that represent vectors. Anyways, so you might be wondering, why would I go through all the effort to do all this trigonometry to generate a random direction to create our particle velocity with, instead of just picking an actually random velocity? So, I've seen this in a lot of games, and I think I actually used to do this myself, where you just pick a random number for the x and y coordinates, and the problem with that is the way it's distributed and scaled. So, for scaling, you run into the problem where if you're going diagonal, let's say you pick the random number from -1 to 1 for both of the axes. Let's say you go into the 1, 1 direction, so +1x, +1y, and that's your velocity. So that's moving twice as fast, if you think about it, because it's going diagonal, as if you were to go just straight right from getting 1 and 0 as your velocity. And the effect that that creates visually is that if you spawn a ton of particles like that, it will create a weird explosion in the shape of a square instead of a circle. So that's the problem with the scaling. Technically, you could normalize those numbers using square roots and stuff in order to make it so that the scaling's correct and it is the shape of a circle, but then you still have problems with the way that it's distributed, like the way that particles get randomly distributed. So to do it correctly, if you want to spread something out in a circle, the best way to do it is to pick a random angle in polar coordinates and then convert that into Cartesian vectors for velocity. So that's a bit of math stuff, and it's really important to, at least when you get into more advanced topics in game development, if you want to make your stuff look natural and look good, a lot of times you do want to get into the math to make things look a little bit better than what the primitive solution might be. And that's just another random tip I'm dropping for you here. And actually, I've just noticed a rather large mistake I've made here. And this is just a side effect of how I'm making these tutorials. This whole section here is actually for the burst, and not for the stream. So if you remember, I said I want a stream of particles and a burst of particles. So technically, this part right here is the clause that's for the stream, so it's just anytime that you're in the middle of the actual movement of a dash that we would run this code. So for that, we'll actually want to take this, and we'll want to create another one of it modified for the stream. But since I just went and did all the math and explained that for the circle, I'm going to add the extra case for the circle here. So we'll do, so if abs self.dashing in 60, 50 for I in range 20, and this is what I was talking about when you do a bunch of particles. We'll say if our dashing is in 60, 50, this means if we're at the start or the end of our dash, we'll do this 20 times. We'll create 20 particles in random directions with random speeds, and that will be our burst. All right, so now we can grab this and go ahead and fix the stream stuff over here. So that's going to be, we just drop it right here and boop. And same thing, except with some minor differences. So p velocity will have to be different this time. We'll do p velocity equals, and we'll say the absolute of player dot dashing, or the absolute of self dot dashing, divided by self dot dashing by random dot random by 3. So if you remember, an absolute divided by itself is just giving you the direction 1 or -1, and then we just take the random number times 3, so it'll be just random number from 0 to 3 in the direction that we're dashing. So that way the stream of particles moves along with the movement a bit, instead of just staying stationary. And then we don't want any movement on the y-axis, because you dash on the x-axis, so we don't want that to be moving around. Anyways, so we'll keep everything else the same. And that should cover that other type of particles. So we have the stream particles, and we have our dashing particles or sorry, our burst of particles right here. So now if we go ahead and run the game again, we can run around. If we press X, oh, whoops, we're not supposed to have leaf. So that's a fun mistake you can make. We're supposed to swap this with particle. Wait a second, what's this game? That one's supposed to be leaf. This one's particle. Wait, why is that one? Aha! So if we go over to here, when I copied this at the beginning, I left that as loading from the leaf. So we want that to be actually particle, not leaf, and that should fix our dash. So if we go back over here, and you can run around and you dash, and you get your start, you get your end burst and your line, but you don't get the start one, which is not intended. So to fix that, there's an important lesson to learn here, and that is that the order for some of these things does actually matter. So if you think about it right here, we're setting it to 60 in our dash, and then say after a dash we get to our update function at some point. So it goes through this update function, and we have our code here that adjusts our dash basically timer thing. So it'll go from 60 to 59 or negative 60 to negative 59. And by the time it gets down to here, but to this code, if it were set to 60, it would have been pulled away already, so it'd be at 59. So this is one of those situations where you can either take this code and move it up, like up here, or you can leave it as is and then change these numbers. Because technically this 50 for the end of the dash is also wrong. It would be 49 if it's right here. So I'm going to do the easy thing and just copy this and move it over here. I think it reads nicer to have the number 1650 as opposed to having to figure out why it's -1 in the future for some reason. So we can now dash, and we get both ends of our dash, which is great, and we have our line between just as we wanted it. And that should cover pretty much all of the movement stuff that we'll be doing, at least for the player. At this point, we have most of the base of the game done in terms of the movement and the basic implementations of the standard things you would find in a game, like animations, particles, physics, etc. But it's time to turn our game into an actual game. And to do that, I think it would be fitting to have some enemies to fight. And the objective would be to defeat all the enemies and then move on to the next level without getting shot. Alright. So to start adding enemies, we'll do something very similar to the leaf spawners thing we have here. And we'll extract a different type of tile and use that to spawn things. So I'll demonstrate how you can add your own, I guess, spawners for the player and the enemies. But then I'll quickly switch to using the pre-made levels I have, because I don't want to sit here for an hour making levels. Alright, so first of all, let's extract some spawners, and then I'll go ahead and add them to the level data itself. So let's do for spawner in, just like the tile, well, just like the leaf spawners, we'll do self.tilemap.extract, and then we'll do spawners 0 and spawners 1. Those will be the tile IDs we're looking for. And this time we don't want to use the whole keep thing, because keep is used to, well, keep the tile in the tile map. If we don't set keep to true, it will actually extract and remove the things that we're asking for. So we actually don't want these spawners to show up in our tile map. We want to just get the location so that we can put stuff there. And that way it works as a spawner as intended. So we'll do if spawner variant is 0. This will be the player spawner. We'll do self.player.position equals spawner position. And then else, we'll just print out the position. Alright, and I'll say enemy. And then we can fill that in later. But for now, let's actually update our map here. So to do this, we can go back over to our level editor. Just go ahead and run this. And let's see if we actually have it in here. No, we don't. So we do need to load in the spawners. So if you look right here, we have decor, grass, large decor, and stone. If you go over to tiles, we have this extra one called spawners, which have a picture of the player and a picture of an enemy. So what we'll do here is we'll say spawners and then load images, and then we'll do tiles/spawners, and that will give us what we need for that. Now if we run this again, we now have the player spawner. We can put it off grid, and we can drop one down there, and then we can go ahead and add a couple enemies as well. And I'll press O to save, and let's go ahead and run the game. Alright, so now spawned us in the right location, and if you look down here, it gives us the 2 locations of the enemies that we added. So with that, we can now actually spawn the enemies. To do that, we obviously need some enemies to spawn. So similar to the player, we're going to go over to entities, and we're going to add a new entity. Alright, so let's add class enemy. And this will inherit from physics entity, same way the player does. And then we'll do definite game, position, size, all that good stuff. Alright, and then we can do super.init game enemy position size. Alright, so with the enemy, we'll use the custom enemy animations, which are over here in entities, enemy, and it has an idle animation and a run animation. So let's go ahead and load those in. So we can just do enemy/idle animation, load images, entities/enemy/idle, and then we'll say image duration equals 6, similar to the player's idle animation, and then we'll also have an enemy run animation. We'll just swap these 2 idles for run, and then we'll set the duration to 4, similar to the player. Alright, so now we can go back over here, and here's the idea for the enemies. They should be able to walk around, but then not walk off of the edge of an island. They should be able to turn around, and we just have a basic AI for just walking around kind of casually. And then it should also shoot at the player if that's appropriate. So that would be based on the location of the player, so whether or not the shot will line up. So the enemies will only be able to shoot horizontally. So it'll have to see if the player's within range and at the right level on the y-axis. But for the actual movement itself, it's going to be kind of like a Koopa. So if you've seen Koopas, they just walk back and forth, and then if they walk up to an edge, they'll turn around. So part of that pattern for AI is to keep track of whether or not it should be moving. So normally there's like a attribute or something that will keep track of whether or not it is moving and for how much longer it should be moving, and then you just randomly decide when it should be moving. Or you can have like a global timer where it's like if it's like you mod it by however many frames, and then you say if it's in this section of that modulo, then you're walking. So it could be a consistent pattern, but I would like the more random pattern, so we'll just use randomness in a timer. So that timer will be self.walking. And this will be similar to dashing in the sense that it's a timer, but this time we won't include direction because we'll derive it from the flip of the entity. Alright, so the first step here is we'll do an def update self tile map movement equals 0, 0. And if you look at the player, these are the same arguments we have here. So if we want to do the physics movement and stuff, we'll need this super.update thing. So we can drop that in right here. So this is just calling the parent update function from physics entity, which handles the physics, as you know. We pass in the tile map and the movement we want to do. So we can modify the movement here to be whatever we want. So before we actually move, we should do some calculations to determine what we should be doing this frame. So we'll do if self.walking. We'll do a pass for now, and then we'll have an elif random.random is less than 0.01 self.walking equals random.randint 30 to 120. So what we're doing here is we're saying if we're walking, we have this space to do whatever we want, which we'll fill in later. And then otherwise, if we're not walking, basically, we can check if this random number is less than 0.01. Since random.random is random number between 0 and 1, that means that this has a 1 in 100 chance of occurring, which, since we're running at 60 FPS, that's 1 in every 1.67 seconds. if we're not walking. So that's how long the average delay is before walking. And then our walking will be set to this random number, which is the number of frames we will continue to walk for. So that's a random number between half a second to 2 seconds. All right, so from here, for the walking, we'll need to do a couple things. We'll start by making it so that it can just walk in one direction and that's it. We'll do movement equals movement 0 minus 0.5 if self.flip else 0.5 movement. So what we're doing here is we're saying that we want to subtract 0.5 if we're flipped, that's facing left, or otherwise we want to add 0.5. So if movement's just given as 0, because that's what the keyword is, then it'll be negative 0.5 or 0.5 depending on what the flip is and if we're walking. And then it'll just keep whatever the y-axis movement was. Now, the next step here is to take the walking thing and reduce the timer. So walking equals max 0, self.walking, you've seen this before, -1. So that'll just cut it down to 0 over time if we're walking. So let's go ahead and actually spawn our enemies. To do that, we'll have to go ahead and import our enemies, and then we'll need to go over to our spawn code right here, and we'll say we want an enemy with the game. We want to give it the spawner's position to place it, and then we'll say it's 8 by 15. You can look at the image yourself and go compute what the dimension should be, but I'm just writing it down here since it's not actually teaching you much. All right, so we also want a self.enemies to add this to. So we'll do self.enemies.append, and we'll add in the enemy. So now with our list of enemies, we need to render them. So I would like them to be right after the tile map, but also still before the player. So we'll do for enemy in self.enemies.copy, because we're going to be removing from that later. We'll do enemy.update. This is the same update code from before. And then we'll give it a default movement of 0, 0. And then we want to do enemy.render, and we'll give it self.display, and the offset will be the render scroll. All right, if we run this, you can see that they're up there and they're walking around. It should walk off the edge because we have, well, yep, they can walk off the edge, and that's what we want to fix. All right, so to do that, let's go ahead and go back to our enemies here. And we want to say, if there's a solid tile in front of where you're walking to and below, meaning that you're about to walk onto a floor, you can keep walking. Otherwise, you need to turn around. So to do that, we need to add some case right here under if self.walking. But we also need some way to determine if there's a solid tile right in front of it. So to do that, we'll go ahead and head back to our tile map, and we'll add, I think, what's going to be the last function for this video. So let's add a def solid check. So this is just checking for a solid tile, and we'll give it a position. It will compute the tile location as the string of the int of the position 0. We've been through this before. Self.tile size plus semicolon plus string int position 1 self.tile size, and that will give us the tile location. If you remember, this is just converting our pixels into the coordinates of the grid system, because we were looking up tiles that you can collide with, which have to be on the grid. All right, so we can do if tile location in self.tilemap, if self.tilemap tile location, type in physics tiles, return self.tilemap tile location. All right. So we're looking to see if this location exists, and then if this is a physics tile, which we have defined up here. So there's 2 types of physics tiles. We have grass and stone. Those are the things you can actually collide with. So we want to see if it exists, and if it's a physics tile, then we return that tile data. In our case, we're not going to actually use the tile data for anything. We're just going to check if it exists, because if it doesn't hit this line, then it'll return none. So we can just put this behind an if statement, since none evaluates to false. as a Boolean, this will be either true or false depending on whether or not something was found. So we can go ahead and use this function now. We can head back over to our entities. And right here we can add that special case I was talking about. So we'll have if tile map, remember we have it passed in right here, which is convenient, dot solid check, and we'll do self.rect center x. And this is where the math gets a little bit funky. We're using some magic numbers and stuff. It's based on the movement. So remember we have this -5 positive, well, -0.5 positive 0.5 depending on flip. We're doing the same thing here, except it's more extreme. We're looking 7 pixels to the left or to the right based on the flip. And that's from the center. And then the next step is to take the self.position 1 plus 23. So that will be below the player in the ground. So this is just kind of scanning out in front of wherever you're facing and then into the ground. And it's taking this location and looking to see if there is a tile there. Now we have this as an if statement, and if it evaluates true, that means there's a solid tile and that we should be able to move. Otherwise, this will do self.flip equals not self.flip. So you just flip it around if there's not a tile there. The side effect of this is that depending on how far you're looking ahead and the tile size and stuff, it could theoretically end up in a situation where you're standing on a tile and just flipping back and forth constantly because there's nothing on either side. So you do have to be careful about that stuff. It's good to think about what your environment is when you're doing these types of things. Like, for example, right now, we have the code for not walking off the edge and turning around when it gets to the edge, but we don't have anything for if it hits a wall to turn around. I can write that up here in a moment, but I don't believe, yeah, they're both on a flat surface where they would walk down as opposed to up, and there's no walls for them to run into. So this is not the greatest example of running into walls, but all we have to do for the walls part is just take this part right here, just grab this, we say if that, and walking, you can drop it right here. If that's the case, then you just do the flip. So we're saying if you run into something on your right or your left, you turn around while you're walking if the solid check passes. Otherwise, you can walk. There's better ways to close this so you don't have to indent it as far, but I'm not going to bother with that. Anyways, that should handle the movement. So let's get into the animations here. So we'll do, this is pretty simple. If movement 0 does not equal 0, self.set action run, because you're moving, so you're running, else self.set action idle. And that's as simple as it is. So if you're not moving, set it to idle. This is a lot simpler than the player's animations because it doesn't have jump or stuff like that. So now you can see that they're walking around and stuff. And they turn around when they get to the edge, which is nice. And they kind of walk for random durations and pause for a bit, which is exactly what we wanted. All right. So the next part is to give them a gun so that they can shoot at us. So I'll go to entities again. And for this, we'll need to modify our render function for the enemy so that we can draw a gun on top of it. So to do that, we'll do def render self surf offset equals 0, 0. So this is like we have down here for the player, except instead of hiding it behind something so we can turn invisible, we're just going to take this as is and call the parent function for the rendering. So this is effectively the exact same as not having that function at all. But we're going to add in some extra stuff here because we want to show the gun. So we'll have if self.flip pass else pass. So the gun will need to be able to flip depending on which direction the player is facing. Let's go back over to game and load in the gun. So we do gun, load image, gun.png. It's as simple as that. And then we go back to entities. And we can render this gun image on top of the player. So we'll do surf.bullet. And this is where we're going to have to handle the flipping. Because so if self.flip, that means the gun should also be flipped as well. Because if you're facing left, then the player image is flipped. So since the gun image is facing right by default, we also need to flip that so it's facing left. So we'll do pygame.transform.flip. We've seen this before. Self.flip game.assets gun, and then we'll say true on the x-axis, false for the y-axis. So this is flipping on the x-axis. We'll do self.rect.center_x -4. This part is just to offset the gun so that it's put in the right spot. You can play around with this number to visually see how it changes. It's just moving it by 4 pixels. And there's just a specific spot I want this placed at. And then we'll do -self.assets gun.getWidth. That's just accounting for the width of the gun image, because we want to render this from the perspective of the top right of the gun image when the gun is facing left, and the top left when it's facing right. So subtracting the width accounts for that. This is another thing we should just kind of play with the numbers and see what you get so you understand. And then, so this last part is the offset of the camera. So this is the same thing used on the player's rendering as well. And then we can do the y-axis, which is rect.center y, and we don't touch this, we'll just do offset -1, so we don't want any funny offsets there. This is a 188 character line of code, so this is a bit long. Remember, if you get it lost on this, go ahead and check out the reference files in the description. So the other side's a bit easier because we had to do special math to do with the flip, plus the actual flip transformation in there. So we'll do something a lot simpler for this one. So surf.blit self.game.assets gun and self.rect.center x +4. So this is the other direction, so we want +4 instead of -4. Minus offset 0, that's the camera, self.rect 0 or rect.center y minus offset 1. All right, so this is much simpler. It's the center with just a 4 pixel offset and the camera, and that should render our gun. That was a bit hectic, but here we go. Oops, I must have written self.assets somewhere. Where did I do that? Ah, yes, this should be self.game.assets. All right, so I run it, and they're holding guns. If you notice, the guns are held out in front of the enemies. They're floating for now, but it'll look a little bit better when we add the outlines later. And they're a bit small, but that's because it's pixel art. In proportion to the player, they're probably the correct size. It's just a small aesthetic thing that we wanted to tack on. Now, the next step is to make these guns shoot. So the way this is going to work is that not that we have a gun object that can shoot, but instead we're going to make it so that the enemy renders the gun image and then also generates the bullets. Before we can actually have our projectiles, we need to create something for them to be stored in the game itself. We also need the image for the projectiles. So for this, we can just copy the gun thing and say projectile, and just copy that over there, and we're good. So that has the projectile image. You can look in the files if you want to see that. So let's go ahead and add the projectiles. So I'm gonna drop them right around here by the particles. We'll do self.projectiles equals boop. So this is gonna get pretty messy here. We're gonna go down here right below the player because we want the projectiles to be on top of the player, but not above the particles because we want the particles to be on top of the projectiles. So we'll go right here and we'll say for projectile in self.projectiles.copy, because we're going to be removing these later. And we'll say projectile 0, 0 plus equals projectile 1. So what we're going to do here is these projectiles, we could make them objects, but since they're so simple, it's easy to just give it a list. So what it'll be is an x coordinate, a y coordinate as a list for the first value. So here's what it'll look like. We'll have x, y, and then we'll have direction, and then we'll finally have a timer. So all we have to do is modify, since these bullets only fly horizontally, we modify the x position. Actually, this would be a list because we're modifying it. We're modifying the x position based on the direction. So we grab the position, we say the x component, and then we add the direction for the movement. And then we can do projectile 2, this is the timer, plus equals 1. And then let's grab the image here. We want to shorten this to image because we're going to be writing this a bunch. Alright, so let's draw the projectile. So we'll do self.display.blit image projectile 0, 0 minus minus image.get width divided by 2. When you subtract half of the width of something, that just centers it, at least if you're doing that for rendering. Because it's based on top left, if you subtract half the width, it's top center. If you want to do the height too, it'll give you the true center, which we will also do. But first, let's add in our render scroll here so that the camera's applied. And then we'll do projectile 0, 1 minus image.get height divided by 2 minus render scroll 1. So something important to remember here is that if you're like adding something new into something like a world where you have a camera like this, oftentimes if for some reason it doesn't appear, it's because you got your camera stuff wrong. So make sure that you're always thinking about how the camera should apply to whatever you're working on. If you're working on, say, like a HUD element, so like maybe a health bar or something that's popping up in the top left of your screen, you don't need to apply the camera scroll to that. But if you're working on something in the world, you need to apply the camera scroll. And then there's the other way around, where if you're working with something in the world and you want to convert something that was in the units of the screen space into the world space, you have to apply it backwards. So it's just something always important to think about. All right, so we're rendering our projectile here. So the next step is to make it disappear if it hits a wall. So we'll do if self.tilemap.solidCheck. This is the same thing that the enemies are using to determine whether or not they should turn around. We'll do projectile 0. So this is the location of the projectile. So we're checking if the location of the projectile is a solid tile. And if it is, then we want to remove it. So all we have to do is self.projectiles.remove projectile. And then we can add some effects here later, but we won't for now. Now the other case, and this is why we have a timer, is because if it just flies off the edge of the map, we don't want it flying forever, because then if it just keeps flying, it never disappears, and as the game runs longer, you'll get more and more projectiles, and eventually it'll lag out because there's too many projectiles. So what you do is you say projectile 2 is greater than 360. So what we're saying here is if our timer, which is, this is the reason we added it, is greater than 360, which is 6 seconds, then we can do self dot, and this is just this code. So we just remove the projectile again. All right, so let's add one more thing. We'll do elif. We want to add something that checks if it hit the player, because it's a projectile that's supposed to kill the player. So we'll do abs self.player.dashing is less than 50. So what we're saying here is that if you're not in the actual moving fast part of the dashing animation, so if it's either on cooldown or if it's at 0, then we do the rest of what we're about to do here. So this check is just to make it so that when you dash, you're actually invincible. And that's how a lot of games do stuff like that, so it's a fun little mechanic. All right, so now we need to check if the projectile hit. So we can do self.player.rect.collide point, and we give it projectile 0. And if that collides with the projectile's position, we know that it's hit the player. So from here, we can do, once again, removal of projectile. So this will work for now. We could print something out if we wanted. Later on, we'll add some visual effects and make it so that it actually kills you and there's a transition and everything, but we'll get to that in a moment. So let's go ahead and run this and see how it's working. Actually, wait, no, we can't yet. We need to add the projectiles. We need to spawn them. So for that, we go over to the enemy. And instead of using like another random factor, the way we'll do this is that when it decides to stop walking, after walking is when it'll shoot. So this adds a more consistent behavior to shooting, because in games it's nice if enemies have some way of indicating that they're about to attack. So in our case, it makes a lot more game design sense to line up the shooting with some sort of predefined action. So if, for example, which is what we'll be doing here, you shoot after you're done walking, then the player has all of that time where the enemy is walking to get out of the way. So it's a little bit of a warning for the player and adds a bit more depth to the game. So what we'll do here is we'll say if not self.walking, so If you notice, this is under the if self.walking clause. We're saying if not self.walking. This is because we have this code right here, which is running down the timer. So we'll get one frame where it passes this statement, then it modifies it to go to 0, so it'll go from 1 to 0. And so it'll pass this, and then it'll pass this, so that we can get to this part of the code. And this is where we can add this once every walk cycle effect of spawning a projectile. So in order to actually shoot, like I mentioned before, we need to check where the player is and whether or not we should shoot. So first of all, let's calculate the distance between the enemy and the player. So to do this, we'll do dis equals self.game.player.position0 minus self.position0, and we'll also just do a self.game.player.position1 minus self.position1. So this is just the difference between the player's position and the enemy's position. So from here we can determine if we should be able to shoot. So we'll say if the absolute of the distance is y-axis, so that's how far apart they are on the y-axis, because we're taking the absolute. And we'll say if this is less than 16 pixels, so if the y-axis offset between the player and the enemy is less than 16 pixels, now we need to run some other checks. So we need to check if self.flip and dis0 is less than 0. So if you look at this, think about it. So if the player is to the left of the enemy, you will get a negative number, because say, well, to the left would be, say, 0 pixels, and the enemy would be at 10 pixels, so you would get 0 minus 10 is a negative number. So if dis0 is less than 0, that means that the player is to the left. And the flip, when true, means you're looking left. So we're checking if we're looking left and the player's to the left, then we should be able to shoot. And the flip side of this, pun intended, is if not self.flip and dis0 is greater than 0, so if the player is to the right and you're looking to the right, then, or rather the enemy's looking to the right, then it can also shoot. So we'll do self.game.projectiles.append, and this is just that list data, remember, so it's position, and then its direction with speed included, and then the timer. So we'll just do self.rect.center x minus 7, self.rect.center y. So this is going to spawn it to the left because we're facing left, because we don't want to spawn the bullet exactly inside the player. We want it to be cast out a little bit. All right, and then we give it our speed, so it'll be facing left, so it's a negative number, and then we give it 0 for the timer. And then we'll copy this, and then we'll do the same thing for the right direction. We'll do plus 7 instead of minus 7 because it's right, and then we'll also make the speed 1.5 instead of negative 1.5. All right, so that should create our projectiles. So let's go ahead and run the game and see what we have. All right, so we have 2 enemies here. Might be a bit difficult to get them to shoot at me from here, so we'll get over here. So you saw the projectile just briefly there. My body blocked it, so that shows you that that was working. I guess technically on this map, there's nothing for them to shoot at because, well, there you saw a projectile go off to the side there, but there's no walls for them to shoot at. So this is not the greatest example for walls, but there are walls on the other maps that they can shoot at. Anyways, so I actually can't get up to this other one up here, but this one is shooting correctly. So if you notice, if I'm in the right spot when it stops walking, so I actually have to be kind of level with it. So if I'm standing down here, it won't shoot. But if I'm level with it, or close to level, it will shoot, and it'll create that projectile, which can hit me, and we can trigger something off of that, like dying, for example. So let's go ahead, since we have all of this working, we can go ahead and load in the custom maps that I had pre-made. So if you look in our files here, so we have all these images, but we also have this maps folder, which has 0, 1, and 2. So I'm going to actually create a function called load map here. We'll call it def load map self map ID. Actually, let's call it load level. And then we'll do self.tilemap.load. And we'll do data maps. And then we need to add str map ID plus .json. So whatever map ID we give it here, it could be an integer, it'll convert it to a string and it'll load that map. Now the other thing to keep in mind is that when you load a map, especially since we're going to be loading maps multiple times because you want to change to different maps, we're going to need to clear out all the particles, all the projectiles, and all the visual effects and stuff, and just reset everything. And then we also need to reload like the player position and everything. So these things right here, these spawners need to be copied down, and the projectiles, and the scroll. So all of this needs to be copied. So we'll just take that, delete it. We'll go over here to load level, drop them right there, and that should load it in with the level. And now instead of doing this tile map.load right here, we can do self.load level, and we'll give it 0. So now this should load one of the pre-made levels that I have. You can look into these files if you want. You could copy them out and rename them map.json if you want to open them up in the level editor as well to see what they look like in there. But we'll be running this from here. So let's go ahead and run that. And we have this nice little map. If I stand right here and wait for him to shoot at me, you can shoot at a wall and you can see that the projectile disappears. So that's the test case for that. And we have, this one's a lot more nature filled than the other test map that I had. And there's this little rock section over here as well. But it's a pretty nice map. There's a few enemies hanging around. So the next thing I want to do is to add some visual effects here. Because if you notice, when I get shot, it doesn't look too nice. The projectile disappears. If the projectile hits a wall, it just disappears. And also when they shoot, it just makes the projectile appear. So that doesn't look fancy enough for me. So we're going to do a little bit of trigonometry here and start making this look fancy. So the way we'll do this is we'll add something called the sparks. This is, I guess, one of the most common things you'll see in my games nowadays in terms of visual effects that distinguishes my games from other games. Because there's a very particular way that I do these that just kind of stands out, I think. I don't think it necessarily looks that good compared to other methods. It's just that it's kind of distinctive, so I can look at games and clearly see a difference based on the fact that I use this technique. All right, so these spark effects should be above the projectiles but below the particles. So we'll do for spark in the self.sparks.copy, and we'll do this similar to how we do the particles, or not the particles, the projectiles, where we wrote the code for managing it first and then added the data. So this time though, because it's so much more complicated than projectiles, we will be creating a class for it. So we'll just do similar to the particles here. Actually, we'll do kill equals spark.update, and then we'll do a spark.render self.display offset equals render scroll. This is the basic rendering stuff. And then if self.kill, we do the basic self.sparks.remove spark. So this is just keeping track of the individual spark visual effects that we need to render. So it'll update it, determine if it should be removed, render, remove if applicable. So this is just a self-managing thing right here. All right, so now that we have this, we need to have this spark object that we're iterating over in our self.sparks that we're calling .update on. So we'll have to add that in now. So we can do this as a new script. So we'll go new file, we'll say spark.py, and we'll do import math, import Pygame, and we'll do class spark. This one won't inherit from anything because it's pretty basic. We'll do an init function. We need a position, an angle, and a speed. That's all we need. If you look at my actual games where I have this effect, I'll actually add more options to the spark. This is about as bare bones as you can get for sparks. Normally, I will have all sorts of things. You can configure the size and how fast they decay and stuff, but I don't want to get too much into it here. We'll just kind of assume a lot of things in our update function, and a lot of the sparks will look the same. All right, so we need to apply our position equals list position, and then we need self.angle equals angle, self.speed equals speed. And then we need an update function. This will be easy. If you remember, we did that thing with particles where we converted polar coordinates into Cartesian coordinates using cosine and sine. So this time, instead of just doing one conversion and being done, we're storing the position in Cartesian, but our angle is polar. And our speed is the length part of the polar coordinate. So The angle and speed together, represent the polar coordinates for the velocity vector, essentially, if you want to get technical about it. To handle that with our Cartesian coordinates position, because you need that for rendering, we do plus equals math.cosine self.angle by self.speed. Remember, if you're doing polar to Cartesian, you just do cosine for the x, sine for the y, and you're pretty much done. And then you multiply it to add in the length. But similar to the particles thing, the reasoning for using polar coordinates here is so that if you're moving diagonally, it doesn't move faster. But then there's a second use case here, which is where when we get into the trigonometry of the rendering for the spark, you need the angle that the spark is facing. Technically, you could just store it as a velocity and then convert that back into an angle so you can do the rest of the math, but it's easier to just keep it as an angle and then deal with that later. So the way these sparks will work is that it's a white diamond shape, a very long but thin diamond, basically, and it'll move in the direction of its angle, but then slow down. And as it slows down, it shrinks. And once it stops, it disappears. So the size of it should be proportional to the speed as well, so that it shrinks down as it slows down. That way, once the speed runs out, it would have just smoothly disappeared because it just would have shrunk to an infinitely small size. So we'll do self.speed equals max 0 self.speed minus 0.1. So if in effect the speed is its timer. So we'll just subtract 0.1 from the speed every update and return not self.speed. So once the speed is 0, we return true, which is the kill signal, which will remove it from the list of sparks. All right, let's do a render function, and then we pass in a surf and offset, same as we always do. And we'll take, this is where the trig comes in. We want render points equals, and what we'll be doing here is we're going to create a polygon. So, and then we'll use Pygame to render that polygon. I'll go ahead and render the polygon with this code, assuming this is filled out first, so they can see what we're doing. We'll do Pygame.draw.polygon. We'll give it the surf. We'll make it white. We'll give render points. So Pygame.draw.polygon will take a surface to render to. It'll take a color that it'll render the polygon as, and then the list of points that create the polygon. So this polygon is automatically closed. Your start point and end point don't have to be the same point. So if you're running a square, you have 4 points, not 5. So it's actually the 4 edges. Now, there's an extra argument here if you want to use it for the width, but we don't need to use that. If you don't specify a width, it'll automatically be filled in. And that's actually a lot of the shapes work. The rectangle is the same. If you render a rectangle using Pygame.draw.rect, if you don't specify a width, it'll fill it in. If you do specify a width, it'll just draw the outline of the shape and not fill it in. So you can do some other visual effects there if you set a specific width. All right, so let's fill in our points here. So we need to create that thin diamond shape based on the angle of the spark. So if you're facing right, you should have a horizontal spark. If you're facing up, it should be a vertical spark. So to do that, and that's not just the 2 cases, it needs to work for any direction. To do this, we'll do self.position 0 and plus, and if you remember, when you want to apply a rotation for a movement, so if you want to move in this direction or something, remember you do the math.cosine of the self.angle, and then you multiply by the speed. So in this case, normally if you want it to be like 5 pixels out, you just multiply by 5. But since I mentioned before that the speed is going to shrink, and as the speed shrinks, the actual spark should also shrink, we're multiplying this coordinate by the speed. So what we're doing is we're actually casting these points out from the center of the spark by adding the cosine of the angle times the speed. So there's other stuff I'm about to do here to create this shape. It's going to get pretty messy here, but we're going to cast them out in the 4 directions. So when you have angles, if you remember, a full circle is math.pi times 2. So if you want to, for example, cast out a point behind you, you do plus math.pi because that's half a circle. So it goes around half the circle and it just points in the opposite direction. If you want to go out just 90 degrees in a direction, you can multiply by 0.5. So that's a quarter of a circle, so it'll just rotate 90 degrees. All right, so that's roughly how that works. So I'm gonna get in and do the messy part here. So we're gonna multiply the speed by 3 because we want one part of the spark to be longer than the others. So we don't want a square, we want a diamond where 2 of the ends are way further out than the 2 sides. And then we need to apply the camera offset, so that'll be minus offset 0. And then we do self.position 1, and as mentioned before, we just do math.sine, same thing. Self.angle by self.speed by 3 minus offset 1. All right, so we can take this, we copy this, and then this is where we start getting into the different angles here. So we have this one right here, since it's using the angle that the spark is, this is the forward point. So this is the one that's being tossed out in front of where the spark is going. So now let's do one that's either to the right or to the left. You actually don't have to think about which one this is because we're going to go do both sides. The order does matter, but only in the sense that you don't want to do opposite ends next to each other because you have to go all the way around. Otherwise, you get a weird shape when you try to draw the polygon. You'll get like an hourglass shape, I think, if you do it out of order. But you can go either way. You can go clockwise or counterclockwise. It's just important to not do opposites next to each other. So we do plus math.pi by 0.5, so it's 90 degrees offset. And then we can just copy this, go over to the sine, so that's the y component, and do the same thing. So that's another offset angle. So we're casting it out to the either to the right or to the left. And then the next step here is to make it, because this is one of the side points, we don't want it to be cast out as far. So we'll switch this 0.3, well, we'll switch this 3 with 0.5 so that the ends are going to be 6 times longer than the sides. So now with this, we can just copy this, both of them, because for this we'll do plus math.pi and plus math.pi. So this third one right here, this is going to be the one facing in the opposite direction from where the spark is going. That's why you're adding half a circle to the angle. And then we keep the times 3 because this is another long one. And then the next one's a short one. So for this one, we can subtract math.pi. The other option is to add 1.5 times math.pi, but subtraction looks nicer to me, so we'll do that. So this will be the 4 sides, so we get forward, and then this gets a bit weird because of Pygame's coordinates and math coordinates are not the same. So one of them is this side, backwards, and then the other side, so this creates a full diamond. All right, so I know this is also kind of a bit of a mess of long lines here, so you can check the reference code if you made a mistake here. You can also play around with this to create some other shapes and some other nice effects. Anyways, this is all we need for the spark, so we can take this and we can start adding it to things. So let's first add it to the enemy. So when the enemy shoots, it should create sparks from the gun. So the way we'll do this is we'll just go right here, and we'll just do for I in range 4. So we want to do something 4 times. We'll just do self.sparks.append spark, and we do need to import spark, so we'll go up to the top here and we'll just go boop, 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 spark, spark, and that'll import our spark for us. So we can go back down to here now, and we can finish our spark. So it needs the arguments. If you remember, it's position first. So for this, we'll just take wherever the last projectile was spawned, so self.projectiles -1. We'll take the coordinate component, because if you remember, this part right here, the first part is the coordinates, so that's the location of the last spark. You could just like copy this out, write this as a position and reuse it here, but this is another way you can make this work. And then we'll take random.random -0.5 plus math.pi, comma 2 plus random.random. So you can see VS Code telling me what these are. So we have the angle here. So what we're doing is we're taking a random number and then subtracting 0.5. So it's a random number between -0.5 and 0.5, and we're adding math.pi to it. So this is the projectile that actually is shooting left. So the angle for left is math.pi. So that's because the right, just pointing right, the angle for that is 0. If you look into unit circles, that's how it is, although it's upside down in Pygame for some stuff because of the fact that in game development the y-axis is flipped. So, but either way, the opposite direction from right is going to be math.py. So what we're saying here is a random direction in the direction of left plus or minus 0.5, so there's random variance, but still pointing left to some extent. And then we'll also take 2 for our speed and add random.random, so there's variance in the speed of our sparks here. So this will cover that, and then now we can go over here and do the same thing, except we don't need that plus math.py because we want it to face right instead of left. All right, so this will cover our spark spawning for the shooting. So the next part is the spark spawning for when it hits stuff. So let's go back over to the game where we have this code for the projectiles. And we'll say in here, if it hits a wall, we want some more projectiles. So we'll do 4i in range 4, so 4 sparks again. We'll just append them. And similar to before, we'll need to go ahead and import these sparks. I'll just copy the import statement up here. And we'll go to the top of game, drop it right here, scroll down, and we now have this loaded correctly so we can do other stuff here. So we'll just take the projectile 0, since we're not using the last projectile anymore, we're just using the current one that we're iterating over. So the angle should be this component, and then we want to do a bit of a funky thing where we do plus math.py, but only if projectile 1 is greater than 0. So what we're saying is that we want to shoot the sparks left only if the projectile is going right. Because when you hit a wall, I mean, there's 2 ways to do this. I like the style where the sparks bounce in the opposite direction when it hits a wall, because that's where the sparks would reasonably go. You could also go in the direction of the projectile, so you can flip this around if you wanted, but I like it this way. So we're saying that it bounces back to the direction it came from, is where the sparks will go. And then we'll take the speed as well, which will be the exact same speed thing from before, which is just random number from 2 to 3. And this will cover the wall case. So the last one I want to deal with, and this is going to be the big one, is when the projectile hits the player. So what we'll do here is 4i in range. We're not going to do 4, we're going to do 30. We're going to spawn 30 sparks here. And for this one, I'm going to write out the arguments beforehand. So we'll do angle equals random.random by math.py by 2. Remember that full circle is 2 times pi. So random.random times that will give you a random angle in a circle. And then we'll do speed equals random.random by 5. And then we'll just do self.sparks.append spark. And we'll say self.player.rect.center. We can give it the angle, and then 2 plus random.random. So the other thing we have to do here is not only are we adding the sparks, but we might want to add the particles. So this is the death, so there's going to be a lot of stuff going on. You can do self.particles.append. Do we have particles in here? Yes, we do. Particle, self.game, particle, so this is the black one, self.player.rect.center, the velocity equals math.cosine, you've seen this before, plus math.py by speed by 0.5, math.sine, angle plus math.py by speed by 0.5. So this is what the speed is for. So the speed right here is randomly chosen for the particles, but I'm reusing the angle for both the sparks and the particles, but I added math.py to the angle here so that the particles shoot off in the opposite direction of the sparks. Anyways, so that's the mess of visual effects for that. Actually, there's one more we gotta do. There's the frame. So we'll do frame equals, and we'll do random.random 0 to 7. All right. So once again, go ahead and check the reference code for this section if you're a bit lost on this because the lines are a bit long. Let's go ahead and run this. So there should be lots of sparks now. I gotta wait for one to stop walking while I'm up here. Hey, turn around. It's gonna shoot. Oh, we crashed. Enemy has no attribute sparks. Okay, so that was a mistake. So that's going to be over here. We have self.game.sparks, not self.sparks. Because this is from the perspective of the enemy. Right. And enemy has no attribute projectiles. Yeah, that's going to be the game.projectiles. Let's see if we got it this time. Hello? No. That kill. Yeah, that's not self.kill, that's kill. Okay, so you saw there was stuff there. So a couple things happened. There was the sparks, which are working when it shoots, but then it crashed when it hit me. So, game has no attribute game. So, what we did here, this should be self, not self.game. And that should fix that. And we should be able to get shot and explode. So you saw there was an explosion there, which is great. Let's see if I can, let's see if I can get him to shoot the wall. So I need him to turn around, there's a wall to the right. If I can get him to shoot there. If he will walk. Will he walk? Let's see. Come on, you gotta go a little bit further than that. There we go. So now if I go down here, we can see if it hits the wall. And the sparks bounce back the other way, just like we added. Alright, so it is possible to get hit. We'll have to add dying later, but first let's make it so that we can actually kill the enemies. So to do that, we use the dash stuff here. Let's go over to our entities. Let's go in the enemy update function, and let's go over to the bottom here, and we'll say if abs self.game.player.dashing is greater than or equal to 50, so that if you're in those frames where you're actually moving in the dashing thing, then we can do if self.rect.collideRect self.game.player.rect. So we're checking if the rect of the enemy collides with the rect of the player, that's like if their hitboxes collide, then we know that they touched while the player is dashing, which means that the player hit the enemy with a dash. So now we can do something based on that. So what we'll do is if we go back to our game here, we have our enemy code. We want to say, similar to everything else, kill equals that. If kill, self.enemies.remove enemy. And then we can go back over to our entities here and we can just return true if we want, because we're in the update function. If we return true, it'll remove the enemy. So all we have to do here is, since they touched, return true. And this is where we get into the mess of visual effects again. So I'm going to cheat a little bit here. I'm going to grab the visual effects that we used for the player's death. I'm gonna copy them, go over to here, paste, and it will have the same effects. So there's a couple things we do have to fix here. So this is referencing self.player because it's from the game's perspective. Fix the indentation. This should be self.game.player. And then this should be self.game. And anytime where we have .player, it should be .game.player. So this is a long thing right here. Just run through it real quick, make sure we got everything. Yep, that should be everything. Now the last thing is that I want to add two big sparks that shoot out from the sides when you hit the enemy. So we'll do self.sparks.append, and we'll do spark self.rect.center, and our angle will be 0 because that's to the right, and then 5 plus random.random, so that's a much higher speed, which means the sparks will be much bigger and go much further. And then we went the other direction, which is going to be math.pi, so that's just right and left sparks that are very big that we want to add. So the last thing here is that actually these are in these particles and sparks are in terms of the player. This should actually be the enemy. So we just chop off the player part, so we didn't actually need that player part. So we want to spawn the sparks and particles based on the enemy's position when they hit, and then that should be good. So let's go ahead and try to delete one of these enemies here. Dash through it. It crashes. Not ideal. Alright, so we go over here. Other mistake. This should be self.game.sparks and particles. Now let's try that again. Suboptimal. What this time? We have, oh, right here also. Alright, one last time. I think this should be correct. Dash through, and they disappear. Perfect. So you get those two sparks shooting off to the side, which look nice and fancy. And you can, like, destroy them and everything. So, boom. So we can kill the enemies. That's great. The last thing is that we want to make it so that the player can die. So we can get shot and it does the particles and everything, but the player needs to be able to die and the level needs to be able to restart. So to do that, we'll go ahead and add a dead attribute here. So we'll do self.dead equals 0 in the game's load level function. We'll have dead equals 0. So this will just be set to 0 by default when you start the game. And when the player is hit by a projectile, we want self.dead plus equals 1. And here's where the magic comes in. We'll go over to the top here and we'll say if self.dead plus equals 1. So it starts at 0, so this won't add initially. But once you're actually dead and it's a positive number, it'll keep adding to it. And then once self.dead is greater than 40, self.load level 0. So all we're doing is we're creating a timer that starts as soon as you die, and after 40 frames, so 2/3 of a second, it'll load the level again and restart you. So for this, all that's left is to actually make the player disappear when it's dead. So all we have to do is head over here and say, if not self.dead, then you can do all these player things like moving around and rendering. So let's go ahead and test this out. So let's get shot. Hello? Nope. There you go, I got shot. So if you notice, you got the delay where you can see the body disappear and the explosion of sparks, and then the level reloaded. So if I actually kill one of these enemies here, and then if I go die to the other one, you'll notice that the one on the left will respawn. And then I will respawn at the start of the level because I reloaded the level, and all the stuff for like spawning the players, spawning the enemies, loading all the tiles, clearing all the particles, and everything occurs when you load the level. So that's a nice reset for us. So that covers everything for the more gameplay stuff here. This is probably the last big thing that we had to do for this project. The rest is just easy stuff to make the game look nice and just kind of polish it off. So congratulations for getting towards the end of this very, very long tutorial. Definitely the longest I've ever done. So I just noticed that I forgot to add the part that handles the case where you're just falling off the edge for too long. So let's say you just run off the edge. You're stuck like this. The only way to get out of this is to close the game and restart it. So that's something that needs to be fixed. And to do that, it's a really, really simple trick. All you do is you just go in here, take the airtime. If self.airtime is greater than, I don't know what a good number is. So let's say you're in the air for 3 seconds, so 180. We do self.game.dead plus equals 1. Simple as that. Actually, we don't want to do plus equals 1 because this is something that will activate constantly once you're past a certain point, which means the death time will last longer. Actually, you know what? That would be fine because you're probably going to be off screen because of the falling anyway, so we'll do plus equals 1. Actually, I think 120 would be a better number. The other thing we have to do before this will work is we'll have to go over to the game and we need to find the player. Say self.player.airtime equals 0. Because we don't want it to trigger multiple times. Alright, so let's just jump off the edge here and see what happens. Alright, so it spawns back, which is good. So that way you can't just fall forever, and that fixes that issue. Alright, so the next thing we'll want to do is start to get into the polishing of the game. The thing that I had in mind for this part is the screen shake. So the screen shake is a pretty simple concept. There's a couple ways you can do it. So one way, well, I mean, obviously it's just a screen shaking supposedly. One way is to modify the scroll value for the camera so that the camera's moving around suddenly. The other technique, which is a little bit more convenient, I feel like, is to modify just this number right here. So when we're scaling up our display onto our screen for the pixel art, we blit it at the coordinate 0, 0. So if we just change this number, let's say we put 50 right here and run the game, you'll see that we've got this black bar on the edge. We can move where we're rendering this thing. So we can like put whatever we want right here, and this could effectively be our screen shake by just changing these values. So we can just take these numbers and generate a screen shake value from them. So let's see here. Let's create self.screenShake equals 0. And over here, let's do self.screenShake equals max 0 self.screenShake minus 1. And that will make it so that the screen shake value is like a timer. We've done this before a bunch of times, that goes down to 0. And if it's positive, we want to offset our screen by it. So this is pretty simple. We just do screen shake offset equals random.random by self.screenShake minus self.screenShake divided by 2. And this will just make it so that you get a random modification in pixels from the number 0 to whatever the screen shake value is. You can just drop screen shake offset right here, and this will offset our screen with the screen shake value. Alright, so now we just need to apply our screen shake. This is pretty easy. Let's find somewhere where we want it to be applied. So right here, when the player gets shot, we'll do self.screenShake equals max 16 self.screenShake. This is so that it essentially sets it to 16, but if it's higher, it won't actually pull it down. That way that a larger screen shake won't be overwritten by a smaller one. Also, something to note is that this is kind of like the speed thing for the sparks, where the effect is increased as the timer is higher. So the offset here is going to be greater when the screen shake number is larger. So it kind of eases off, but you give a big number, it gets a large screen shake and lasts longer. All right, so let's take this and let's copy it over to the enemy code. So let's go into the entities and let's go into the enemy update function where we have the killing based on the player's dash. We can just drop it in here, and this is the self.game.screenShake because we want there to be an impact when you hit an enemy with your dash and destroy them. So now the last thing is when the player's falling, which we just added, you want to do the same thing. You want to screen shake there. We've got to be careful with this, so this should be hidden behind a if not self.game.dead. Actually, no, technically you wouldn't need that because I just remembered the update function won't be called if you're dead, but whatever, I'll leave it there. It's no big deal. All right, so now you should get some screen shake. Boom. So you can tell the screen's shaking when I hit them. And let's get shot real quick. Just show the other case. Boom. All right, so yeah, there's a fair bit of screen shake, which is a very nice visual effect. It adds a lot of emphasis to the different actions. And it's a really simple effect to add it, as you just saw. So I like to add it in a lot of my games. So we actually have our different levels here. If you look in maps, we have 3 of them, or rather I made 3 of them for you to use. But there are 3 maps, and right now we just have it hard-coded to just load the first one. So the next thing is to make it so that you can actually beat a level and transition to the next one. So the way you can do this is by, well, when you beat it, you just call self.loadLevel. You've seen how when you die, you have to just reload level 0. So now we can just take a level variable and use that to load the next one. But I want a fancier transition, so it won't be as simple as just writing a couple lines to just once you win, move to the next one. We're going to have a proper transition, so there'll be a timer and everything. So for that, let's go ahead and do a self.level equals 0 just to start us off, and we'll use this whenever we reload a level. So we can do load level, find the other use case, which is right here, and we can just copy in that self.level value. So now we can keep track of what level we're on with self.level. All right. With that, now we need a transition variable. Self.transition equals -30. This is on the load level. So whenever you load a level, I want the transition to be -30. The way I want this to work is that we'll have a circle of what you can see that shrinks down at the end of a level and then grows bigger at the beginning of a level. So between those two, after it shrinks down, it's a completely black screen, and then at the beginning of the new level, it's also completely black screen, but then grows into a scene where you can see the full thing from that circle. All right, so the idea is that when it's at -30, you want to show a completely black screen, and it'll go all the way up to 0 for full visibility. And the way we'll make this loop is that it'll go from 0 at the end of a level to 30, which is when you get the black screen, so it'll shrink down. It's a bit difficult to explain, but you'll see it as I implement it. So let's go over here into run. And I'll just start writing the logic and I can explain it better once you can see what I'm doing here. So we'll have if not when self.enemies. So if you've killed all of the enemies, we do self.transition plus equals 1. And then the other case is if self.transition is less than 0, self.transition plus equals 1. So what we're getting here is that it starts at -30. It goes up automatically until it hits a transition equals 0, and it won't go any higher on its own. And then, once there are no enemies, this will automatically increase transition even more past 0, and then once we're up to 30, then we can do self.level plus equals 1, and self.load-level self.level. So the way this will work is, like I mentioned, start at -30. This is the beginning of a level. Your vision goes bigger until 0, and then anything above 0, and it shrinks. So the way you can think about this is that when the absolute of the value of the transition is 0, that's when you see everything. When the absolute value of the transition is 30, that's when you can see nothing. The fact that I'm using the negative and positive numbers is just a trick to keep track of the state of their transition mathematically the way you need it to be. Because another thing you have to think about is that you have to load the level when it's black, when it's completely black. Because when the view is shrinking down from the old level, you don't want to transition to the new level yet. You want to still be seeing that old level. And then as soon as it starts opening back up again, you want to be seeing that new level. So it's a smooth transition. So it's important to get this right when it's at the full black screen. So yeah, that's how that's going to be implemented. All right. So the next step is to actually visually implement this. So what we'll do is we'll do if self.transition. We'll do transition surf equals pygame.surface, and this is where we'll do a bit of some graphical magic. We'll do self.display.getSize. So this will just create a black surface, the size of our display, and this is what we'll use for the transition. So the trick here is we'll draw a circle on the surface, and then we'll set the color key of the surface to the color of the circle. That way that the circle we draw is a transparent part. So if we blit this surface on top of the screen, you'll just see the outer edges that aren't inside the circle. So that'll give us the effect we're looking for. And we just change the size of the circle. So we can do pygame.draw.circle, transition surf, that's the destination. So we're not drawing something onto the screen for once, we're drawing it onto something else. And then we'll draw this thing, which we're drawing onto our screen or display or whatever. And so this is going to be white, like I mentioned. It just needs to be a different color than black. It can be anything, because we're going to color key it. And then we'll do self.display.getWidth divided by 2, self.display.getHeight divided by 2. So pygame.draw.circle will draw a circle, and all these draw functions are like this. It takes the surface, then the color, and then the extra arguments. Usually if there's a singular position, this is where you'll find it. So in our case, we have the center of our circle, and then now we have to give the radius. So the radius will be, oh, and here it's telling us, so you can read that if you want. So our radius will be 30, because that's the number we were choosing before. We could change this number if we want the transitions to be faster or slower. And then we'll do minus the absolute value. Remember I was talking about the absolute value of the transition, of the self.transition. And then the trick here is to multiply this by 8. So this comes from the dimensions of the screen, so you can do the math and do 30 times 8 and you get 180. So this is just to make sure that the circle can expand to its proper size and everything. So also, if you notice, this is clause behind the self.transition, so when you're not transitioning, when it's at that 0 and waiting for you to beat the level, it won't run this code. And that's because this code is actually a little bit expensive in terms of performance, because you're generating another surface, drawing a bit circle, and then blitting it onto the display. So it's an extra step we can cut out to save some performance if we want. So we'll do transition surf.set color key, because we just do the circle onto it, and we want this thing to ignore the white color, so that will become transparent now. And then we just blit it onto the display and just throw it at 0, 0, because it's the same dimension as the display as specified here. All right, so now if we run the game, And if we defeat all the enemies, it should theoretically transition, if I did it right. Let's see. And there you go. So we got the circles, and here's the second level. So you can just like run through it and try and kill all the enemies, and there's 3 of them, which I think I'll save the 3rd one for the end here. But something interesting to note is that I don't have the... Let's see if I can go and shoot at me. I just accidentally dodged them all. The transition applies differently when you're dead. So one hacky way we can deal with that is to go over to this right here and say if self.dead is 10 or 30, because if you notice, self.dead actually goes for longer than the other transition stuff. Actually, no, it should be 10. We'll do self.transition plus equals 1, and actually it should be greater than or equal to 10. And then what we'll do is we'll actually take this, cut out the plus, and just do self.transition plus 1, and then we'll take the min, and we don't want it to actually go across 30, because that will trigger it to add to our level count. So we don't want that. We just want the transition to go as high as it can without actually going to the next level. So what we'll do is just lock it right before we go to the next level, so that it's mostly done the transition, so it looks nice, but then it can stay on the same level. Oops, there's a typo in there. Where is that transmission? That's not correct. All right, let's try that again. There's one more issue we'll have to fix here. There we go. So that's working as intended. So we get ourselves our nice transition here when you die. But there's one more thing we have to fix, and that's this thing right here. We load the level by adding 1 to it, and the problem is this level can go too high. So what we'll do is, this is just kind of to stop it from crashing. Theoretically, you'd add more levels and extend this however you'd like if you wanted to make this a full game. But in our case, I'm just going to do something to prevent it from crashing. And we'll just take this and we'll say the min of self.level plus 1 and len os.lister data /maps. And we got to import os to do this. But the way this will work, where we go, import OS. The way this will work is it's capping this by using min to the number of maps that we have. Although actually, now that I think about it, this should actually be -1 because we have 3 maps, but since we started at 0, the highest value is 2, so we don't want to go above 2 if we have 3 maps. So you just do -1 there if you're naming them like this. All right, so I won't run through that right now because that would take a while to actually run through the whole game, but you'll get to see this cap later on when I finish the game and run through the whole thing. But for now, I can just test it to see if it's still moving to the next level. And that's how I would know and test these things, because technically that line of code doesn't execute until you finish a level, and as you saw, it just worked properly there, so that's good enough for us. So let's go ahead and take that idea of rendering onto a surface that isn't your display for some graphical effects purpose, and let's take that to a whole nother level here and have ourselves a bit of fun by adding some outline visual effects. So to do this, we're going to need a second surface. And to do this type of thing in general, these types of visual tricks, a lot of it actually comes down to creativity more so than knowledge of the tools that you're using. I mean, you have to know how to use the basic functionality for your tools, but a lot of it really does come from the creative application of the basics. But this is just another example of something that I came up with a long time ago, and it's fun to use. Anyways, so to do this, we need a second display, so we'll do self.display2 equals pygame.surface. It'll be the same dimensions, so 320, 240, and we'll do pygame.src alpha. Actually, wait, sorry, I had this backwards. Also, there's no underscore in src alpha. I feel like there should be, but there isn't. Anyways, so we'll drop it right here. We're actually on display. Display is the one that needs it, not display2. So the way we're going to break this apart is that we'll have display and display2. So display is the thing that most of the stuff is going to be rendered onto. The naming here is slightly misleading because we're trying to make the code that we already have work for this. And this is just kind of a finishing touch. And this is something I actually recommend if you're making games. If you're almost done with a project, you can kind of just throw code cleanness out the window, because if you're not going to be working on it much longer, it's not too much of an issue. And this actually applies to a much broader section of game development than just the end. There's this funny idea that I heard a long time ago, is that there's two types of game developers. There are game developers that write good code, and there are game developers that release games. And funny enough, I actually have not released a big game since I started writing good code. Some of that is because I got a bit too much into trying to do things properly, and then some of that is just kind of other stuff going on. But overall, don't worry too much about your code structure, especially if you're working by yourself. As long as your stuff works, a lot of times it's not as important as people think it is. Also, there's the whole performance component as well, so you do have to keep that in mind. But let's move on here. So we have our two displays here, and the way this is going to work is that we render most of the stuff as normal onto the display, and we want to give some things an outline, not everything. So the way this will work is that the stuff that we want to give an outline will render onto display, and the things we don't want to give a background, so we'll do this for the particles and the background. For that stuff, we render it onto display 2. And the way this will work is that between those layers, so there's the back layer and the front layer. So there's the background, which won't have an outline. Then there's the foreground, which is going to be the particles. And before the foreground is drawn, we need to add our outlines. So there'll be a step right before the particles where we turn whatever we've drawn onto display into an outlined version of itself. So the way we'll do this is, first of all, we need to break up our rendering here. So we'll go down to where we render our background, and this needs to be display 2 now, because we're drawing the background and that shouldn't have an outline. And now self.display needs its own color, and this needs to be transparent because we're going to be doing some tricks here. So we're filling display with pure transparency. So if you put it on top of something else at this point, you would get nothing. But anything we draw onto this will not have a black background. It'll just be whatever we draw onto it, we can just put onto something else, and that's what we'll get. Anyways, so the next step is to jump over to that spot I was talking about. So we'll find the part right before the particles. I do want to include the sparks with the outlines because I like how that looks. But we'll need to create a display mask, and we'll do equals pygame.mask.fromSurface. And we'll pass in the self.display. So what we're doing is we're making a mask from the display, which is where we're rendering everything that we want it to have an outline. So if you don't know what a mask is, a mask typically, it can mean multiple things, but usually in computer graphics, a mask is essentially like an image with just two colors, black and white, or you can think of it as on and off, ones and zeros, however you want. But the idea is that you can do binary operations on them, but in our case, we're actually using it for something different. We're using this to convert something that has multiple colors, like tons of colors, into something that only has two. So what we'll do here is we'll create display silhouette. That is a very difficult word to spell sometimes. Thank you, French people. I'm assuming it's French. And we'll do display mask. So this is a mask we created. Remember, think of it as two colors, white and black. And then we'll do to surface. And actually, in terms of Pygame, it'll call it the set color and the unset color. So set color being kind of the white portion. But what we'll be doing is we'll do set color equals 0, 0, 0, 180. And then unset color equals 0, 0, 0, 0. So if you don't know, when you see four colors like this is red, green, blue, and then alpha. So the alpha is the transparency. So if it's 0, it's fully transparent. That's what we did when we filled the display up here. But 180 means that it's slightly more leaning towards opaque rather than transparent. So that 128 would be halfway because it's 255 is the max. And these first three are just saying it's black. So right here, it doesn't matter what the first three are because the last one's transparent. But for this one, it does matter because, well, that's going to be black. So this is going to be the color of our outlines. And the way this works is from surface, well, actually, if I have it, it says this. So it takes a surface, and then it will either use a threshold, which you can specify for what gets categorized as set and unset. But if you have a color key set, or if you have transparent pixels, it'll just take those and use that as unset. So in our case, because we filled it with this transparency, anything that's transparent will be unset. So what we get as a result is anywhere where we rendered something before is the set color, which means that it can turn into this. So now what we get is just kind of blobs of black wherever we drew something. So to kind of show you what this looks like, I'll do display 2.blit display, actually self dot, and then we'll do silhouette, and then we'll give it 0, 0 for now, and then we'll change that later. So if we run it right now, we get an interesting result. So you've seen this before. This is where everything's just kind of lagging behind, and we're not clearing the background properly, so we do need to fix that. The problem here is that we're rendering display instead of display 2, and we should be rendering display 2 when we're over here, which I forgot. But now you should see, here we go. Here's just the silhouettes of everything we're rendering. So you can see what's going on here. It looks like a nice fancy effect, but we're gonna use this for the outline. So the way this is gonna work is if, for example, let's do the next important step here, which is display 2.blit self.display 0, 0, 0, or 0, 0. So it's just drawing it back on top. So this is just putting whatever we drew in this frame back over on top of the display. So we rendered our silhouette, and then we're rendering our stuff we rendered again. So if you run this again, you just get the game. And that's because this stuff is perfectly covering wherever we drew our silhouette. So if we want to see where the silhouette is, we can just do like 4, 4 or something. And you see we get that outline sticking out. Well, it's not outline, it's a drop shadow kind of. So there's a funny little shadow on everything now. But we don't want this shadow in particular, we want a proper outline. So to deal with that, we draw this 4 times. I'm going to replace those coordinates with offset, and we'll do 4 offset in, and this is where the magic comes, -1, 1, 0, -1, and 0, 1. And if you do that, you render it 4 times with an offset of these amounts. That'll do 1 pixel in each direction, so it's left, right, up, down. You get an outline. So now if you look at this, we have ourselves a nice fancy outline. Although now that I'm looking at it, I don't like the outline on the clouds. So let's go ahead and take display 2, which is the one that doesn't get the outline. This is the output. And when we render the clouds, we just swap that with display 2, and we can go ahead and run this, and our clouds no longer have the outline. So it's just the actual foreground stuff that has the outline, which looks really nice. And the sparks also have the outline and the projectiles, but if you notice, the particles do not. And it's important because the particles are already black themselves, so you don't want to mix it in there. Otherwise it'll look funny. The particles will be weird shapes. So it's better if you just don't do the outlines on them. It doesn't look out of place, like I said, because they're black, so that's convenient. All right, we have ourselves our nice outline effect. There's lots of different things you can do with masks as well that are quite fun. I recommend playing with this thing as well to try to figure out and understand fully how it works if you don't quite understand. Like I mentioned, there's a lot of stuff you can do with masks. If you look through my games, you can see me doing all sorts of random things with it. It's just a nice graphical tool. I think in Pygame, one of the best uses, which funny enough is not what they're, I think, usually used for. One of the best uses is to actually just compress an image down into 2 colors so you can do some type of thing. But one of the more common use cases is to do intersections with masks for pixel perfect collision. They allow for binary operations where you can say, if this mask is set in a location and this other one is, then it'll be set. So that way, if you have like a player's mask and an entity's mask, you can check for a pixel perfect collision by overlapping them and seeing where they're both set. And there's all sorts of stuff you can do that people use them for, but this is an interesting graphical trick. This is making use of just Pygame's abstraction for them for how it can efficiently convert this into a surface. There are ways to do this by hand, or not by hand, manually, where you're setting pixels, and it would be super slow. So this is just the fast way to do it. All right, that's pretty much it for the outlines though. Okay, we're in the final stretch here. The last thing that I wanted to add to this game before I would say we're done is to add the sound effects and music. So for the sound effects, it's going to be pretty simple. We just do self.sfx equals jump pygame.mixer.sound. So this is how you load a sound in Pygame. You just do pygame.mixer.sound, and then you just give a path to the sound. So we'll do data sfx jump.wave. And then we'll just go through and then do this for our different sounds. There's ways you can optimize this so that it's more extendable and takes less code, but I'm not going to worry about that because this is meant to be a simple example. So I'm just renaming all these and making sure we're loading all the things we need. So we have dash, hit, shoot, ambience, jump. Those are our sounds. So you could add more if you wanted. And then I'm going to tweak our sounds a little bit. So we're going to have self.sfx ambience.set volume 0.2. And we're going to go through all of them and adjust them. So these are just going to be constant values that determine how loud each sound should be when we play it. Normally, when you have sounds like this, they're not going to be quite at the right level for what you're expecting in the game. It's best for your sounds to be as loud as possible when you load them in, and then you just scale it down because you can't scale it up. So we'll do 0.4 for shoot and 0.8 for hit, so 1.0 is the max. We'll do 0.3 for dash and 0.7 for jump. So the quietest sound is going to be the ambience, the loudest sound is going to be when something is hit, and then the second loudest sound is going to be your jump. So we're just kind of organizing it like that. I have already gone through beforehand and make sure these values sound good, so you can mix it however you want. But that should cover the loading and configuration for our sounds. So I'm going to go ahead and add the music actually. So the music's going to be pretty simple. Let's go ahead down to run here. We'll do pygame.mixer.music.load. We'll do data music.wave. So for audio files in Pygame, there's quite a few supported technically, but some of them can have issues when you try to package the game into an executable. I know that I've had issues with OGG or OGG files, whatever you want to say. I've been meaning to look into it and figure out what the solution is to get this to work because they're a much smaller file size. But if you want things to work well, it's just best to have everything as a WAV file. And then Pygame works well with that, and then the packaging works well with that. I believe there's some restrictions on what can use different file types. So the music player and the sounds have different restrictions for what file types you can use, but you can look up the documentation to see that. They actually might be the same nowadays, I'm not sure. I know that there's some rules on the different operations you can do because, for example, I believe on MP3s there's some weird stuff with the way they're compressed that affect which types of things you can do it on it. So there's stuff for controlling playback, like you can fast forward and pause and play and do all sorts of stuff. So certain things might be restricted on certain formats and stuff like that. But all that's on the documentation, so you can look into that if you're interested. Anyways, so I just use waves for everything. If you're concerned about file size, you can look into some of the other solutions, but waves are high quality audio-wise, and then they run fine for most use cases, so that's usually my preference. All right, so we'll do music.set for volume. So this is the same as when we set the volume for the sound effects pretty much, except instead of it being a pygame.mixer.sound object, we're calling it right here. So something interesting to notice is that we're doing music.load. So this is not outputting an object. This is actually just meant to be something where you can have one thing loaded for your music, and then we can set the volume for the one music thing, and we just do set volume 0.5, and then we'll do pygame.mixer.music.play. So in the play, there's a couple options here. You could see them right here if you want to look into them. But what we'll be doing is we'll be using -1. So whenever you play a sound or music in Pygame, the .play function can take a number, and that will be the number of loops you want. So if you say 0, it doesn't loop at all. If you say 1, it'll loop once. If you say -1, it'll loop forever. And that's what you want for music. And the other thing we want this on is the ambience. So we'll do self.sfx ambience.play -1. So if I run this, you should hopefully be able to hear it. So there's music playing, and you can hear some birds, which is nice. Hopefully I got the mixing right. We'll see when I'm editing this later. Not that I can change it at this point. But there's the ambience and the music. The next step is to add the rest of the sound effects that we have here. So we have a few of them. We can just look at them, and this is normally how I make games. I go through and add the sound effects at the end. But you can just look through here and kind of add them based on what they're associated with. So like shoot, for example, is pretty easy. You just grab this. So this points to the sound object, and similar to the music thing, you just do .play on it. And we also did that with the ambience right here. So anyways, we just got to find the shooting code, which we know is over in entities. And if we go and find the enemy and find where it spawns the projectile, which is right here, we can play the sound. So we just go right here, we do self.game.sfx.shoot.play, and that will cover what we need for that. And we also have a jump function, so we can actually go down here into, where is it, jump. And well, this is a bit messy. So we have return true. So there's a couple of ways we can do this. We could drop it in all of these 3 cases for jumps, or we can do it the hacky way and go over to here and say, hey, we call jump. We had that whole thing where we return true, so we know if the jump actually went through or not. So we can say if that went through, then we can just do self.sfx jump.play. And now we have the hit sound. So for the hit sound, that'll be for 2 things actually. So the enemies can get hit and the player can get hit. So for the enemies, that's right here. So we just drop that and we just grab hit and play that. And then the other thing is when the player gets hit, and that one's over in the projectile code in the game. So if we go over here, this is the projectile loop. We find where it kills the player, which is right here. We drop this, we say shoot, we play say play. And then we have a couple more things. I think we have dash. Actually, I think this is the last one. So dash is pretty easy. So if we look over here, we have our dash function. So this one doesn't return anything. So we can just drop it here. We could add a return here and do it similar to the jump if we wanted, or we can drop it right here. It doesn't matter at this point. So we'll just say dash.play, and that should cover all of our sounds. So let's just run the game and see how this goes. So you can hear me jumping. It's a nice boop sound. If I dash, you can hear me dash, which is cool. And let's see. When he shoots, you can probably hear it. Sounds like someone just hit a tennis ball. Alright, so if I dash through him, you can hear the hit. Or if I get shot. Shoot. Oh, that just crashes. That's gotta be fixed. So that's just, go over to here. This should not be self.game. That should be self.sfx. And that should fix that. So let's just test that case real quick. And, wait, that was shoot. That should be hit. Okay, there we go. Let's see. We should have it now. There we go. All good. So all the sound effects are in. So the game is technically complete, but there's one last thing we need to do. The last thing that I wanted to do was to make this game into an executable. With Python, we call this packaging. For things like C++, you might call it compiling, but technically with Python, what's happening is that we're taking the Python interpreter, which interprets Python code, and then bundling that into an executable with the Python code. So that way you run the executable and it runs the interpreter and then it runs the Python code. So that's how that ends up working. So the executables kind of have a minimum size based on how much stuff you're including and also however big the Python interpreter is. So I think the bottom end of it is like 20, 30 megabytes or something. And then it'll grow depending on how much you're including. All right. So to get started with this, let's open up a command line. So you can just do Windows key cmd. We've done this before to install Pygame. So it could be your terminal, your command prompt. You could even put PowerShell if you wanted and do it there, but I'll do it in cmd. And we'll just do py-m pip. So it's the same as when we installed Pygame. So whatever pip is for you, and then we'll do install. And it'll be py installer. Make sure you get the casing right on this. It's capital P, capital I, no spaces. And then I already have it. So I'm going to go to navigate to my game. So I'm going to go desktop. It's going to be different for you, obviously. But just navigate to the folder where your game is. For me, this is going to be Ninja Game. And if I do dir here, you can see all my stuff. So this is the same as what I have here on the left. And if I go ahead and do py-m PyInstaller, depending on how PyInstaller installed, you might be able to just type PyInstaller. But for me, I have to do py-m PyInstaller, because PyInstaller is its own module. I mean, we just installed it, so yeah, it's its own module. Sometimes it'll be bound to just PyInstaller, so you could just type PyInstaller. But we do this, and then we have to say the name of the main script that we're running. So in our case, the script that we run to run the game is game.py. So we just do game.py, and this would create the executable. But there's extra arguments you can add here. So there's like stuff for adding icons and stuff like that. There's an icon thing, I believe, in Pygame as well. And then there's the icon that shows up on your taskbar on Windows. I think on different operating systems, what has control over what parts varies. So I think on Windows, that's how it's split, where I think Pygame controls the top left icon on the window, and then on the taskbar, it's based on the executable. But then I think on Linux, it might be, I can't remember if the packaging has full control over it or if Pygame does, but I think it varies by operating system. So if you want to get the icon correct, you would have to do both of those, so you can look into that if you want. So there's an argument for that in PyInstaller. We won't mess with that because we don't have an icon for this game. But there's two arguments that I commonly use. So one of them is no console. So normally if you don't use this and you run the executable, you'll get a window that pops up. It's the console output for the game. So you know how we have this console down here where, I mean, we could print out whatever we wanted and we would see it in our output down here. So it would create a command prompt window, actually not technically command prompt, but like some kind of shell window where you can see the output of the game. So if you don't want that, and you don't want the users to see that extra window in the output, I know a lot of people get confused by it. Most games don't have something like that. So you would just do one file or not one file, no console to get rid of it. And the other argument is one file, the thing I accidentally just typed. So one file will make the whole thing one file. The big thing is that it gets rid of all of the files that Python generates because of it having to include the interpreter and all the packages and everything. So it'll generate like, I don't know, 50 files at a top level, and then there's hundreds or thousands of files lower down that you could dig through that are just all over the place and it looks really messy. But the problem with one file is that the people over at Microsoft have still not dealt with an issue on Windows, where Windows will flag things made with PyInstaller as a virus because people make too many viruses with PyInstaller. So PyInstaller is really popular for, I mean, just making any type of executable from any type of Python thing. So because Python is also one of the most common things used for making viruses, people are usually making their viruses and then packaging them with PyInstaller. So PyInstaller, especially if you do one file, has some very specific things like that kind of identify the executable. It's not intended to identify the executable, but there's certain things that it just kind of tends to put in there because they're packaged the same way that will show up in those viruses for like just the data for that executable. And then anything else you make with PyInstaller that might not be malicious. So in our case, our game. So the people at Microsoft have not figured out that they're hooking off of the stuff that's in stuff made by PyInstaller to detect viruses, which, I mean, to be fair, I guess it does detect a lot of stuff that is made with PyInstaller without them having to recognize it, but it catches a ton of other stuff too. So anything made with one file will fall under that pretty much. So you can remove that, and then because people don't generally make viruses where there's like 50 other files and it has to be in a zip folder and everything, because people don't typically do that, I think coincidentally that whatever that signature is that they're hooking off of from the way that PyInstaller makes things is no longer there. And because the executable is smaller and Windows doesn't freak out as much, sometimes it still does, because I guess maybe some people are still making viruses like this. But this is the better way to avoid Windows freaking out when people download your game and try to play it. So basically you can use one file if you want it to be one file. Otherwise, don't. Either way, this technically doesn't include all of your assets. So a lot of your extra files, so like your images and stuff, aren't included in this. So what you would have to do is you copy them over either way to whatever your output is. But I'm pretty sure there are ways that you can also include other data like images and stuff so that you can properly make the whole thing one executable. So depending on what you're doing, you might want to do that. It's just good to know about. But in our case, because if we ever want other people to play this, we probably don't want them getting as many virus warnings. They'll still get them because that's just how Pygame is. You can do this. And if you really want to get rid of those warnings, one option is, I think, to pay for a certificate with, I don't know if it's with Microsoft or some other organization, to basically prove that your executable is not a virus. I don't bother doing that. And then the other option is that there's some weird tricks you can use with PyInstaller for how it builds things to get it so that it builds it in such a way that it doesn't cause that issue, but it's very difficult for mine, so I don't want to get into the explanation. Or not necessarily very difficult, but it's a bit confusing. Anyways, something else to note is that if you're releasing on Steam, Steam just takes the executable, or actually all of your files, and then you tell it which executable the game should run when they click play. And because Steam itself is just calling the, I guess, the command line or terminal arguments or whatever to run that executable, the Windows warning never pops up. So no matter how you do this, it doesn't matter if you're releasing it out for something like Steam, they're not going to see any virus warning. So this really doesn't matter too much if you're doing something like releasing it on Steam. But let's go ahead and run this, and this will generate our executable. It can take a moment. And while I'm sitting here, something else to mention is that PyInstaller actually works on a bunch of different platforms. So it works on Linux, and it's supposed to work on Mac OS. It's supposed to use the same arguments for them, but I've had some issues on Mac OS. I know I tried with I don't know, maybe it's like a 2008 MacBook, which is like 15 years old now, and I tried that, I don't know, like 5 years ago when PyInstaller wasn't as popular, and I had a lot of issues with it. I don't know if it's fixed now, so I don't know. You can try that and see if that's working. I'm pretty sure it works now, so it should be mostly cross-platform. Not that your executable's cross-platform, but you can build it on multiple platforms. And the way that works is that if you want to build it for a specific platform, you have to be on the platform you're building for. So if you want a Windows executable, you got to be on Windows. If you want an executable for Mac OS, you got to be on a Mac. If you want something for Linux, you got to be on Linux when you run this. So it's kind of a bit of a mess. And just one extra tip for those of you who are considering releasing something on Steam. I don't know if this is still the case, but I know when I released something in like 2018 and 2019, they had a requirement for all Linux games that they had to run on Steam OS, which is the operating system for Steam Machine, which was released a long time ago, and they were still requiring that people supported that in order to say that they supported Linux, even though almost no one uses the Steam Machine nowadays. And that was running on, what was it? I think it's over a decade old, maybe coming towards 15 years old version of Debian, which has some very different requirements for how things run. So if you want it to work on that, you might have to get a really old version of Linux to build on for this to pass Steam's requirements for what counts as Linux supporting. That was a bit of a headache for me. Anyways, we should have our executable built. If we go over to the game folder, we'll see that we have a couple new folders here. We have build and dist. So just ignore build, that's just where a bunch of the build files are. We don't need these. This exe doesn't work on its own. So what we need to do is we actually go over to dist. I think it's for distribution. And there's a game folder here. This folder is actually named after, I think, whatever the name of the Python file you gave it is. And then here's where everything is. So this has all sorts of stuff in it. So these DLLs that I think Pygame's using, and we have like Python stuff. So here's the Python DLLs for the running the game or interpreting the code. And we have like Pygame, NumPy, OpenGL, etc. There's all sorts of stuff in here. Anyways, the thing we want is game.exe, but if we run this, it crashes and says blah 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 blah, can't find this, can't find the decor. So it's trying to load the decor and can't find it. So what you gotta do is you go over to your game and you grab the data and scripts. You don't actually have to grab scripts, but I grab them anyways. And just anything that the game's dependent on. So in our case, it's data and scripts. We're not using map.json anymore, but if we were, we would have to grab that too. But let's grab these two. I'm gonna copy them both. And then let's go over to game, same folder as this executable, because you treat this game.exe like game.py, and you just drop them in here. So the paths need to be the same. So if we refresh now, we have data now, which has all of our stuff in it. And then we also have our scripts, which are there if you want them. Depending on what you're doing, you might have put something in scripts that you might need. So it's worth just throwing in there. All right, so let's go ahead and run our game. And it runs fine. And this is the executable, not the Python script. So this will run even if someone doesn't have Python. So some common issues that can occur are, well, first of all, sometimes there's issues with PyInstaller just installing to begin with. If you have those, you're just gonna have to look it up and try to figure it out. There's all sorts of things that could happen. And then there's random issues that can happen during the build process, which is also usually related to your install, unless you have some weird arguments. And then the last thing that's most common is when you run the game, if it crashes. And so a couple things that can happen here that you can watch out for are fonts. So I don't know if it's still an issue. I know at least it used to be that the system fonts in Pygame did not work in PyInstaller. Another thing, as I mentioned before, is the audio files. So if you use an OGG file, a lot of times it'll cause crashes as well. So there's just stuff to be careful about. And then there's also the whole missing resources thing. It used to be that, and I think sometimes it still does this, it depends on the circumstances, it will just say like failed to execute script and won't give you the information you need, as opposed to doing that thing we just saw here a moment ago where it gives you the whole crash output so you can debug it. If it says failed to execute script, sometimes you can open up a command line, navigate to the executable, and run it from there by just typing the name of the executable. And then if you get that crash, it'll show the output here. I think that's more common if you do one file, is when you would have to do that to see your issues. Anyways, so we have our game here. Let's go ahead and beat it, because we might as well, since we just finished it. And it's an executable for everyone to play. So I'm just going to run through the levels here. So just gotta beat all the enemies, dash through them, don't get shot. Pretty simple. I haven't done this a bunch of times already because I tested this plenty of times while I was initially making this before I did the tutorial. And fun fact, this tutorial's been recorded over the span of, I don't know, 50-something days. And I made this base game well, not a very long time ago, but a while ago. I just messed up. So this one's the last level, it's a bit trickier. So you gotta actually jump over stuff and try to dodge things. You can move right after you spawn, which is an issue that could be fixed, but it's not that big of an issue, so I'll eventually figure this out. A bit harder than I remember. I think the trick is to go right first, but okay, we got those guys, that's the hard ones. There we go. Let's try to not mess it up this time. Alright, there we go. So now there's this little island down here with a couple guys on it. And we have these guys over here. And we just got to get a good dash over on these guys on our left here. There we go, we did it. And if you notice, like what I mentioned before, it loops back, well, it doesn't loop back, it caps it at this third level and you can't go past it. It'll just restart it when you beat it, because that's the last level. So you could add more if you wanted. All right, so the last thing I'll mention is that you can go over to here and send this to a zip folder, and that could be like your game, for example. And you could call this like Ninja Game. So another thing is that, for example, this executable is a bit hard to find for users. So you extract it, you see this mess in here, and you're like, where's the game? So this is the game. I mean, you could rename it to help make it easier to find. Another thing you can do is create a batch script in this folder that executes this executable, so that you can see it'll be like just a folder called like the name of your game or something, and then there's an batch script right here that you could just double click to run the game. If you look at my games, that's how I've got it set up, at least in the more recent ones, so you can go see how that's set up if you want to use that, but I won't teach you about batch scripting here. So that's pretty much everything for just creating something they can share with others. And that's pretty much everything for creating the game. Congrats on reaching the end of this 7-hour tutorial. Hopefully this is just the beginning for you, and if so, you may be wondering what some next steps may look like. The next steps will depend a lot on your skill level at this point. For some, you may have some ideas already for how you could make games at this point without having to depend heavily on tutorials. If so, I recommend you do that, since that's one of the best ways to solidify your knowledge. If you're feeling a bit daring, you could consider participating in a game jam like the Ludum Dare, the Alakajam, or Game Maker's Toolkit. Game jams are a great way to get used to the game development process from the idea to the release stage, and I recommend participating as soon as you think you're able. For those of you who aren't yet ready to make games on your own, don't worry. This is actually the norm when you first start and is commonly referred to as tutorial hell. It's defined by the absolute dependency on tutorials, and in order to get out of it, you have to focus on developing your problem-solving skills so that you can take what you have learned and generalize it into other solutions. This is the essence of what makes an engineer an engineer. In fact, I believe that for most people, you only have to learn the skill once, and if you switch to a different skill altogether, even if it's not even related to computers, you'll learn very quickly. You can improve your ability to generalize concepts best by picking apart things that work and making minor changes to both see what those changes do and to see if you can turn it into something else. Additionally, a sample of one is often not enough to see the abundance of different ways concepts can be used, so it doesn't hurt to check out a few more tutorials if you're still struggling. Don't focus too hard on just Pygame either. Oftentimes people aren't actually stuck with Pygame, and instead they need to learn more about Python or programming. Pygame itself is pretty simple, and there's not too much to learn in terms of its actual functions. It's all about how you take those limited tools and build something with it. There are plenty of functions that Pygame has that I didn't mention in this tutorial, but aside from maybe rotations and text, they aren't really essential. If you want to learn about a few more functions Pygame does provide or some interesting techniques, you can check out my amateur or advanced Pygame tutorial playlists. Alright, that's all I have to add. If you just sat through the full 7 hours and you learned something useful, I'd think that'd be worth clicking subscribe for. This tutorial took quite a bit of time to make. I put out usually rather advanced Pygame related content all the time, so there's tons of other interesting stuff on my channel. Anyways, thanks for watching, and good luck on your game dev journey.